A cosmic accident has created a perfect laboratory for the bizarre. Drifting through the void 420 million light-years away is a galaxy with a tail, a structure so immense it defies belief. This is the Tadpole Galaxy, a spiral torn asunder by a violent collision. Its long, graceful tail of stars and gas stretches for 280,000 light-years, a river of cosmic debris left in the wake of chaos. Within that chaos lies a hidden trove of wonders. We are about to embark on a treasure hunt across this distant island universe, counting down 50 of its strangest and most mysterious objects. By the end of this journey, you will have a front-row seat to the most extreme physics and beautiful violence our universe can muster. What cosmic corpse brighter than a million suns lurks in its heart? Could entire new galaxies be forming inside its tail? The answers reveal a universe far stranger than fiction. What does true cosmic chaos look like to you? Our journey begins at the very center of the chaos, the anchor point for this entire cosmic drama. Every large galaxy is believed to house a supermassive black hole in its core, and the Tadpole is no exception. But this is not a quiet, sleeping giant. The violent collision that created the Tadpole's spectacular tail did something more. It stirred the beast. Imagine a dormant volcano suddenly shaken by a massive earthquake, its vents cracking open to release pent-up fury. The galactic collision funneled vast rivers of gas and dust directly toward the galaxy's heart, feeding the black hole a feast it had not seen in eons. This transformed the core into what astronomers call an active galactic nucleus, a powerhouse of radiation. While we cannot see the black hole itself, its influence is unmistakable. Matter spiraling into that bottomless pit at nearly the speed of light forms a searing, whirling disk of superheated plasma, an accretion disk brighter than billions of stars. From this maelstrom, twin jets of charged particles might be screaming out into intergalactic space, carving through the surrounding gas. The estimated mass of this cosmic engine is staggering, likely weighing in at millions, perhaps even billions of times the mass of our own Sun. Its activity paints the central regions of the Tadpole in a harsh, energetic light, a beacon announcing that the galaxy's heart is very much awake. This awakened core sets the stage for everything else we will find, its gravitational pull and energetic outbursts influencing the strange objects born from the collision's wreckage. What other relics of that ancient crash are now orbiting this furious center? Radiation from that awakened core pours out into the surrounding chaos, but it is not the only source of light in this shattered spiral. The galaxy's main body, the head of the Tadpole, is studded with brilliant knots of sapphire blue. These are not single stars. Each of those dazzling points is a giant star-forming cluster, a cosmic nursery of staggering scale. Born from the immense shockwaves and compression of the galactic collision, these clusters are factories where star birth happens on an epic, almost industrial level. Inside just one of these blue knots, you might find hundreds of thousands of young, hot stars, all screaming into existence at nearly the same time. Their combined luminosity is ferocious, outshining many smaller galaxies entirely. To grasp their size, think of the ancient globular clusters that orbit our own Milky Way, dense balls of a million stars. These Tadpole clusters are their younger, more massive, and far more violent cousins. While globular clusters are old and red, relics from the early universe, the clusters in the Tadpole's head are newborns, blazing with blue-white intensity. They are so bright and so concentrated that they act like beacons, lighting up the entire central region of the galaxy and illuminating the very gas clouds from which they were born. Their intense ultraviolet radiation carves out vast bubbles in the surrounding nebula, shaping the galaxy's structure even as they live their short, spectacular lives. These are not peaceful nurseries, they are the brilliant flashpoints of cosmic rebirth, the first and most visible sign that from great destruction comes new creation. But what of the material that was not compressed into these brilliant knots? what was flung far away by that same cataclysm. Stretching across the void for 280,000 light-years is the galaxy's most defining and bizarre feature, its namesake tail. This is not a mere smudge of light, it is a river of cosmic wreckage, a fossilized record of the violence that reshaped everything. The tail is composed of everything ripped loose during the collision, vast streams of hydrogen gas, fine dust, and millions of stars torn from their original orbits and sent sailing into intergalactic space. The physics behind it is a brutal gravitational tug-of-war. As the smaller intruder galaxy passed through the tadpole's main disk, its gravity did not simply pull, it sheared. Think of it like a stone skipped across a pond, but instead of water, the stone is a galaxy, and the ripples are entire spiral arms being stretched into impossibly long, thin strands by conflicting tidal forces. This process, called tidal stripping, is what sculpted this magnificent arc. But here is where the tale becomes truly strange. It is not a graveyard, it is a cradle. All that gas, compressed and shocked during the collision, has itself begun to collapse. Scattered along the tail's length are brilliant pink knots, glowing clouds where new stars are igniting. This means the tail is a stellar nursery in its own right, a star-forming factory operating in the emptiness between galaxies, far from the crowded galactic center. The iconic Hubble image shows this perfectly, the blue clusters in the head, and then these delicate, glowing beads on a string tracing the long curve into darkness. It is a structure of both destruction and creation, a bridge of newborn suns connecting the galaxy to its own scattered past. Those glowing pink knots are just the beginning. Embedded within the tail's stellar river are even more profound anomalies, tiny islands of sapphire fire. These are not simply star clusters, they are something far more significant, isolated blue dwarf galaxies in the making. Each one is a compact, fiercely luminous region where star birth is so rampant and so concentrated that it qualifies as a miniature galaxy all its own, forming in the emptiness far from any galactic core. This is a staggering sight, a direct observation of galaxy formation happening in real time. We are witnessing the universe build new galactic islands from the wreckage of an old one. The tidal tail provides all the necessary ingredients, vast reservoirs of loose gas and dust, and the collision itself provides the trigger, the shock waves that cause these enormous clouds to collapse under their own gravity. What we see as a brilliant blue speck is a firestorm of millions of young, massive stars, all burning hot and bright, their collective radiation making them stand out like cosmic lighthouses against the darker tidal stream. Their future is a fascinating puzzle. They are currently free-floating, born from the tail's material and moving along with its flow, but gravity is a patient architect. Over billions of years, these infant dwarf galaxies face two possible fates. The immense pull of the main Tadpole Galaxy might slowly reel them back in, causing them to merge with the larger body in a much gentler union than the original collision. Alternatively, they could settle into stable orbits, becoming permanent satellite galaxies like moons to a planet, forever circling the giant that created them. This turns the tail from a mere stream of debris into a galactic assembly line, forging entirely new worlds from the ashes of the old. The brilliant blue knots in the tail point us back to the source of all this chaos. To find the true architect of this cosmic sculpture, we must look not forward along the tail, but backward against the flow of time. There, caught in the gravitational undertow, is the culprit itself, a small, distorted galaxy being slowly erased. This is the infalling dwarf galaxy, the second actor in this ancient drama. It is not a majestic spiral, but a mangled, smeared collection of stars, currently passing through the tadpole's main disk for what is likely the second time. Its fate is sealed. The immense tidal forces of the larger galaxy are actively tearing it apart, stretching its stars into faint streams that are already blending into the tadpole's outer halo. You can think of it as a comet, but instead of a tail of ice and dust, this celestial object leaves a tail of stars and whole star clusters. Astronomers play the role of cosmic detectives to identify this perpetrator. The evidence is in the motion and the wreckage. By carefully measuring the velocities of stars in and around the tadpole, they can trace paths backward, finding the common point of origin for the tidal tail. The Dwarf galaxy's current path, its distorted shape, and the sheer scale of the debris trail all finger it as the intruder. The timeline of the collision is written in the tail's length. The Dwarf galaxy first plowed through the larger spiral roughly 600 million years ago. That first pass is what initiated the stretching, pulling the long tail of material out into space. The Dwarf, slowed by the encounter, then looped back around in a vast billion-year orbit and is now making a second destructive passage. We are witnessing the final stages of a slow-motion merger, a galactic absorption that will, in another few hundred million years, be complete. The Dwarf galaxy will cease to exist as a distinct entity, its stars becoming just another part of the tadpole's growing halo. This raises a profound question about our own cosmic home. Is the Milky Way's serene spiral also the product of such ancient, violent meals? Some of those newborn stars do not stay in the nursery. The chaotic gravitational dance within the tail creates celestial catapults, launching stars into the abyss at unimaginable speeds. These are hypervelocity stars, solitary suns rocketing through the void so fast they can escape the galaxy's grip entirely. The mechanism is a gravitational slingshot. Imagine a binary star system, two suns orbiting each other, drifting too close to one of those dense newborn star clusters in the tail. The immense gravity of the cluster can violently disrupt the pair. One star gets captured, swung into a new orbit around the cluster, while its partner is flung away, recoiling like a stone from a sling. The ejected star receives such a tremendous kick that its velocity can exceed 1 million miles per hour. At that speed, it is not just leaving the tail, it is breaking free from the Tadpole Galaxy's gravitational hold forever. These stars become true loners, destined to spend eons traveling the empty darkness between galaxies, their light a faint, speeding beacon with no destination. The tadpole's tail, with its dense clusters and swirling, unsettled gravity, is a perfect factory for such runaway stars. Visualize a star's perspective for a moment. One moment it is part of a binary pair, the next it is ripped away, accelerating until the entire Tadpole Galaxy, tail and all, shrinks to a mere smudge of light behind it. It journeys into a profound emptiness where the nearest other star may be light years away, a solitary wanderer born from an ancient collision. This raises a haunting possibility. Could a hypervelocity star forged in the tadpole's tail ever streak through our own galactic neighborhood millions of years from now? That solitary hypervelocity star carries a secret with it into the void, a final, fading signature of its violent birth, but other secrets are not so eager to leave. Deep within the tangled streams of the tadpole's tail, orbiting no visible star, is a pinpoint of pure, silent fury. This is anomalous X-ray source 1, a mystery beaming directly at us from across the cosmic ocean. Our eyes would see nothing there, just the faint glow of the tidal stream. But through the lens of an X-ray telescope like Chandra, it screams. It appears as a brilliant, isolated point source, a cosmic lighthouse flashing in a spectrum of light 1,000,000 times more energetic than visible light. This is not the broad, diffuse glow of a hot gas cloud. It is a precise, concentrated pinpoint, telling us the energy is coming from an object smaller than a city, yet shining with the power of 10,000 suns. The source of such intense X-rays is almost always a gravitational monster, a place where physics is pushed to the extreme. The leading theory points to a binary system hidden within the tail's gas. Picture a pair locked in a deadly dance, a normal star like our Sun, and a super-dense corpse, either a neutron star or a stellar mass black hole. They orbit so closely that the intense gravity of the dead star strips material from the living one. This stolen gas does not fall gently. It spirals inward at nearly the speed of light, forming a searing, whirling disk around the neutron star or black hole. The friction within this accretion disk heats the gas to temperatures in the millions of degrees, causing it to blast out those torrents of X-rays we detect. What makes Source 1 so strange and compelling is its isolation. It does not sit in a bright star cluster or a glowing nebula we can easily identify. It is a ghost in the machine, a powerful gravitational engine operating in what appears to be a relatively quiet stretch of the tidal tail. We know it is there by its fierce, high-energy scream, but the exact identities of the dancers in this binary remain veiled. Is the compact object a neutron star, a city-sized ball of pure nuclear matter so dense a teaspoon of it would weigh 1 billion tons? Or is it a black hole, a few times the mass of our Sun, hiding an event horizon from which not even light can escape? The answer is written in the precise flicker of its X-ray light, a code astronomers are still working to crack. This single, anomalous point reminds us that the tail is not just a serene river of stars, it is also a hunting ground for some of the universe's most voracious and invisible predators. Source 1 is not alone in its high-energy scream. Deep within the tadpole's main body, far from the tidal tail, another brilliant and baffling X-ray beacon pulses. This is anomalous X-ray Source 2, a cosmic sibling with its own mysterious story. While both sources shine with ferocious intensity, a closer look reveals they are not identical twins. Source 2 is often brighter, and its light flickers in a different, more erratic pattern. This variability is a crucial clue. The way an X-ray source brightens and dims over time acts like a fingerprint, telling astronomers about the size of the emitting region and the chaotic flow of material onto whatever dense object lies at its heart. The fact that Source 2 flickers differently suggests it might be a different breed of monster, or perhaps the same breed in a different stage of its violent life cycle. What could possibly produce such staggering amounts of energy, outshining entire star clusters in this single, angry band of light? The leading suspects are known as ultraluminous X-ray sources, or ULXS for short. These are objects that defy the standard rules for stellar mass black holes or neutron stars. A typical stellar black hole, formed from a collapsing giant star, might be 10 times the mass of our Sun. Its X-ray output has a theoretical limit, a brightness ceiling based on its mass and how fast it can devour matter. Yet both of the tadpole's anomalous sources, and especially Source 2, appear to blast far beyond that limit. They are too bright to be explained by a normal stellar corpse. This forces astronomers to consider two thrilling possibilities. The first is that we are looking at an intermediate mass black hole. This would be a missing link in cosmic evolution, weighing in at perhaps a few hundred to a few thousand solar masses. It is too small to be a supermassive giant like the one in the galaxy's core, but far too large to be the remnant of a single star. Such an object could have formed in the dense core of a now disrupted globular cluster, or perhaps is a primordial relic from the universe's earliest days, now wandering the galaxy. Its greater mass would allow it to accrete gas at a much higher rate, powering the extreme luminosity we see. The second possibility is just as strange, a stellar mass black hole or neutron star that is not playing by the rules. Imagine a compact object that is not just feeding, but gorging itself, pulling in material at a rate so prodigious that the radiation pressure from its own feast should theoretically blow the incoming gas stream apart. Somehow, it stabilizes, creating a supercritical accretion disk that funnels the energy into narrow, intense beams directly toward us. This geometric beaming effect could make the source appear far brighter than it truly is, like a lighthouse beam blinding you while the lighthouse itself remains modest. Whether they are missing link black holes or stellar corpses in a state of extreme gluttony, These ULXS represent some of the most energetic and poorly understood phenomena in modern astronomy. Their presence in the Tadpole, a galaxy already defined by collision and chaos, feels perfectly fitting. They are the hidden power plants of the wreckage, the unseen engines humming in the darkness, reminding us that true cosmic violence often operates in wavelengths our eyes can never see. While those X-ray sources scream in invisible light, other relics of stellar death announce themselves in more subtle, ghostly forms. Drifting within the tadpole's spiral arms is a delicate bubble of energized gas, a fossilized echo of a star's final, catastrophic moment. This is a supernova remnant, a shell structure expanding silently into the surrounding void. In visible light, it might appear as a faint, circular wisp, a ring of glowing filaments. But in radio wavelengths, it reveals its true nature, a brilliant, crisp shell broadcasting the story of its own violent birth. Recognizing one is a matter of looking for that perfect geometry, a sphere or bubble of emission that stands out sharply against the more chaotic background of the galaxy. This shell is the expanding debris field from a single, colossal explosion, the supernova that marked the death of a star many times more massive than our Sun. Estimating the age of this cosmic ghost is an exercise in cosmic forensics. Astronomers measure two key things: the shell's current size and its expansion velocity. By using the Doppler shift in its light, they can clock how fast the outermost filaments are racing outward, often at speeds of thousands of kilometers per second. Then it is a simple calculation of distance divided by speed. If the shell is 10 light-years across and expanding at 10,000 kilometers per second, the explosion happened roughly 1,000 years ago. This turns the remnant into a time capsule, allowing us to pinpoint a specific moment of cosmic violence within the galaxy's long history. Was this star's death witnessed by any emerging civilizations on planets within the Tadpole? Its light would have outshone the entire galaxy for a few glorious, terrifying weeks. The composition of this expanding shell is the final confession of the star that created it. As the shockwave plows through space, it sweeps up and heats the surrounding interstellar material, but it also churns up the star's own guts, forged in its core and during the explosion itself. By analyzing the specific colors or emission lines from the glowing gas, astronomers can perform a chemical autopsy. Finding abundant oxygen, neon, and magnesium points to the corpse of a star that was between 8 and 15 times the mass of the Sun. Detecting even heavier elements like silicon, sulfur, and iron is the signature of a truly titanic progenitor, a star that started its life with perhaps 20 solar masses or more. Each element is a clue to the star's internal structure and the ferocity of its collapse. This particular shell, frozen in its expansion, is more than just a monument to destruction. It is a vital disperser of the very ingredients for future planets and life. All the iron in your blood, the calcium in your bones, and the oxygen you breathe was forged in the hearts of stars and scattered across the cosmos by explosions just like this one. The Tadpole's remnant is a single link in that grand, life-giving chain, a silent gardener fertilizing the galaxy with the elements of creation. That expanding supernova shell is a monument to a single star's death, but the Tadpole's chaos can forge monsters on an entirely different scale. Tucked away in a dense knot of stars, perhaps one of those brilliant blue clusters, is a gravitational puzzle that points to a cosmic missing link. Stars at the cluster's core are whirling around an invisible point at breathtaking speeds, tracing orbits that scream of a hidden, immense mass. The mathematics of their motion reveals a dark anchor weighing not 10, not 20, but several hundred times the mass of our Sun. This is a candidate intermediate mass black hole, an object that has long eluded astronomers. For decades, we have confidently found two main classes of black holes: the stellar mass variety, born from dying stars and weighing up to about 100 solar masses, and the supermassive behemoths that squat at the centers of galaxies, tipping the scales at millions or billions of suns. The vast gap between them has been a persistent mystery. How do the giants grow from the small ones, intermediate mass black holes, with masses ranging from 100 to 100,000 suns, are the hypothesized stepping stones. Finding one is like discovering a missing chapter in the story of how galaxies themselves assemble. The violent environment of the tadpole is a perfect crucible for creating such an object. Think of that dense star cluster packed with tens of thousands of stars in a relatively small volume. In such a stellar traffic jam, gravitational interactions are constant and fierce. Massive stars can sink to the cluster's center through a process called dynamical friction, where they exchange momentum with lighter stars, gradually drifting inward. Over time, these heavyweights can collide and merge, building up a more and more massive object at the very heart of the cluster. If this process continues unchecked, the resulting object could collapse directly into a black hole of several hundred solar masses, all without the need for a single supernova. Alternatively, a cluster core so dense might see multiple stellar mass black holes themselves merge together, a slow-motion consolidation of darkness that builds a middleweight champion. The candidate in the tadpole offers a tantalizing glimpse of this process in action, a dark seed that could, given enough time and enough infalling material, one day grow into a supermassive giant itself. Its existence whispers that the building blocks of galactic centers are not born there, but are forged in the fiery, crowded nurseries of star clusters and then delivered by the tides of cosmic collision. Amidst the stellar nurseries and dark remnants, a different kind of time bomb ticks. This is a luminous blue variable star, a titan in its final volatile act. Imagine a star so massive and so unstable that it barely holds itself together, a seething ball of plasma pushing against the very limits of stellar physics. These are among the most luminous stars known, shining with the ferocious light of millions of suns. Their brilliance comes at a cost: extreme instability. They do not burn with the steady glow of our own sun, they convulse. A luminous blue variable undergoes sporadic, violent eruptions, casting off vast shells of its own outer layers into space in events that can temporarily double its brightness. The star is engaged in a desperate tug of war, where the outward pressure of its own radiation battles against the immense gravity of its core. This struggle makes it wildly unpredictable, prone to colossal outbursts that pepper its surroundings with glowing nebulae, the ejected material from its previous tantrums. To picture one, we need look no further than our own galactic backyard at the star Eta Carinii. In the 1840s, it underwent a giant eruption, becoming for a time the second brightest star in the entire night sky, despite being 7,500 light-years away. It ejected at least 10 times the mass of our Sun, creating the beautiful bipolar homunculus nebula that now encases it. A luminous blue variable in the Tadpole Galaxy would be a scaled-up version of this same magnificent instability, a beacon of impending doom visible across the intergalactic void. The fate of such a star is sealed and spectacular. It is a prime candidate for a future core collapse supernova, and not just any supernova. Given its enormous mass, it could potentially produce a hypernova, an explosion orders of magnitude more energetic than a typical supernova, possibly accompanied by a long-duration gamma-ray burst, the universe's most powerful electromagnetic blast. If such a star in the tadpole were to erupt tomorrow, the spectacle from our safe distance would be staggering. For weeks, it could outshine its entire host galaxy, a single point of light momentarily drowning out the combined glow of hundreds of billions of stars. It would be a fleeting, glorious monument to the fact that in the cosmos, the most brilliant lives often end in the most violent transformations. But the luminous blue variable is not the only kind of stellar titan writing its fate across the nebula. Within the tadpole's brilliant blue clusters, we find an entire society of monsters, a gathering known as a Wolf-Rayet star cluster. This is not just a group of stars, it is a conclave of cosmic veterans in their final, furious phase. Wolf-Rayet stars are the exposed, blazing cores of stars that began their lives with at least 20 times the mass of our Sun. Through a combination of fierce stellar winds and perhaps violent eruptions, they have completely stripped away their outer hydrogen envelopes like a fruit peeled down to its dense, searing pit. What remains is a naked stellar furnace, a core burning helium and heavier elements at a ferocious rate, with a surface temperature soaring to over 100,000 degrees Fahrenheit. Their most defining feature is not just their heat but their fury. They blast out stellar winds of unimaginable power, streams of charged particles racing away from the star at speeds approaching 3,000 kilometers per second. To put that in perspective, the solar wind from our Sun travels at a mere 450 kilometers per second. The wind from a Wolf-Rayet star is a continuous, supersonic hurricane, carrying away a mass equal to our entire Sun every 100,000 years. This relentless outflow carves the surrounding space into surreal sculptures. The intense ultraviolet radiation from the star ionizes the nearby gas, making it glow, while the physical pressure of the wind rams into slower-moving material from earlier in the star's life. The result is often a complex nebula, a glowing shell or bubble being constantly reshaped by this stellar gale. In visual terms, these nebulae can look like delicate veils, intricate rings, or vast, turbulent clouds, all painted in the vivid reds and pinks of ionized hydrogen and nitrogen, a celestial canvas shaped by pure force. Yet this beautiful violence serves a profound purpose. The winds from Wolf-Rayet stars are not just hot air, they are element factories. In the extreme conditions of their atmospheres and winds, nuclear fusion products are churned up and blasted into space. This includes vast amounts of helium, but also carbon, nitrogen, and oxygen, the very building blocks of future planets and life. A single cluster dominated by these stars acts as a colossal dispersal pump, chemically enriching its entire region of the galaxy at a breakneck pace. Their lives are spectacularly short, ending in just a few million years in the ultimate fireworks show, a supernova or even a gamma-ray burst. But in that brief, incandescent life, a Wolf-Rayet star does more to alter its galactic environment than a star like our Sun does in 10 billion years. They are the great sculptors and chemists of the cosmic landscape, turning their own self-destruction into the raw material for tomorrow's creation. That chemical enrichment from Wolf-Rayet stars settles into the galaxy's dark, dusty corners hidden from our eyes. But one of the tadpole's strangest objects betrays its presence not with visible light, but with a deep, pervasive warmth. This is a mysterious infrared blob, a region that appears as a faint, inconsequential smudge in optical images, yet erupts into a brilliant, glowing hotspot when viewed through the infrared eyes of telescopes like Spitzer or Herschel. The contrast is startling. What our eyes perceive as a dim void is in reality a cauldron of hidden energy, its secrets locked away behind thick curtains of cosmic soot. This is the fundamental power of infrared astronomy. Visible light, with its short wavelengths, is easily scattered and absorbed by tiny grains of interstellar dust, the same dust that creates dark lanes across spiral galaxies. Infrared light, with its longer wavelengths, acts like a cosmic X-ray vision, slipping between these dust grains almost unimpeded. It allows us to peer directly into the heart of obscured regions, to see the heat glow of objects that would otherwise remain completely invisible. The intense infrared signature of this blob tells us one thing immediately: something inside is very, very hot, and it is heating that surrounding dust to temperatures that make it shine in this invisible spectrum. So what is the hidden furnace? Two leading possibilities present themselves, each a testament to cosmic extremes. The first is a massively obscured stellar nursery. Imagine a giant molecular cloud, far denser and more turbulent than average, that has collapsed to form not just a single star cluster, but a veritable factory of newborn stars. Hundreds, perhaps thousands of protostars are igniting within, their fierce radiation trapped by the very dust cloud that birthed them. All that stellar energy is absorbed by the dust, heating it until it re-radiates the energy outward as the brilliant infrared glow we detect. It is a stellar maternity ward operating behind a one-way mirror, its brilliance converted into a warm, diffuse haze. The second possibility is a single, monstrous behemoth, a dust-enshrouded giant star. Picture a luminous blue variable or a red supergiant in a late, unstable phase, violently ejecting its outer layers at a tremendous rate. This ejected material forms a thick, opaque cocoon of gas and dust around the star, a self-made prison that swallows its visible light entirely. The star's immense radiation, however, cannot be contained. It heats the inner walls of its dusty shell to incandescence, turning the entire cocoon into a giant infrared light bulb. We would see no pinpoint of starlight, only the warm, expansive glow of its heated cage. Deciphering which scenario is true requires peeling back the layers with even more precise instruments. By analyzing the exact infrared colors of the blob, astronomers can estimate the temperature of the dust. A broader, cooler glow might favor the stellar nursery model, where heat is distributed throughout a large cloud. A more concentrated, hotter signature could point to a single, central engine. Sometimes, very sensitive radio telescopes can detect the faint whispers of water or methanol masers, natural lasers that often pinpoint the precise location of a massive protostar deep within the murk. This infrared blob is a perfect reminder that our view of the cosmos is limited by the narrow window of light our eyes can see. Beyond that familiar rainbow lies a hidden universe of warmth and shadow, where the most dramatic acts of creation and destruction are playing out behind the scenes, waiting for the right kind of light to reveal their stories. Deep within the tidal wreckage, a different kind of distortion might be at play, one that warps the fabric of space itself. Among the faintest glimmers in the tadpole's tail could be a cosmic illusion, a gravitational lens candidate. This is not an object in the traditional sense, but a phenomenon, a natural telescope created by the universe's most fundamental force. The principle is Einstein's, a cornerstone of his theory of general relativity. Massive objects do not simply pull on other objects with gravity, they warp the very space-time around them. Picture a heavy bowling ball placed on a stretched rubber sheet. It creates a deep depression. Now roll a marble across that sheet. Its straight path will bend as it passes near the bowling ball's well. Light traveling through the universe behaves like that marble. When light from a fantastically distant galaxy passes near a massive foreground object, like a dense cluster of stars or dark matter in the tadpole's tail, its path is bent. From our vantage point, the image of the background galaxy is distorted and magnified. It might appear as a stretched, luminous arc, or if the alignment is perfect, as multiple, identical images of the same galaxy arrayed around the foreground mass like beads on a celestial necklace. Finding such a lensed arc in the tadpole would be a monumental discovery. It would act as a direct natural scale. The degree of distortion, the separation and brightness of any multiple images, provides a precise and elegant way to weigh the foreground object causing the lensing. This measurement includes everything, not just the visible stars and gas, but all the dark matter clinging to that region of the tail. It would offer a clean, gravitational census of mass in a place born from pure chaos. The search is a meticulous one, combing through deep field images for those telltale arcs, those two perfect symmetries of light that cannot be explained by any normal galactic structure. A confirmed lens here would turn a stream of stellar wreckage into a precision instrument, allowing us to peer even further into the cosmic deep, using the tadpole's own distorted remains as a window to galaxies older than the collision itself. The hidden furnace of the core may be launching invisible lances into the void, while the central black hole's accretion disk blazes across many wavelengths. Its most far-reaching influence might be sculpting space in the silent realm of radio waves. Astronomers search for the signature of relativistic jets, twin beams of superheated plasma screaming away from the galactic center at nearly the speed of light. These are not gentle outflows, they are cosmic blowtorches, focused and collimated by intense magnetic fields twisted into tight coils by the black hole's furious spin. Picture the most powerful particle accelerator on Earth, then imagine one nature built that is light years long and powered by gravity itself. Material from the inner edge of the accretion disk, instead of falling in, gets caught in these magnetic field lines and funneled outward along the black hole's rotational axis, launched with unimaginable force. In a settled galaxy, these jets can stretch for hundreds of thousands of light years, punching far beyond the galactic disk into the pristine intergalactic medium. They carve vast cavities in the thin gas that floats between galaxies, heating it and preventing it from cooling and falling back in to form new stars, effectively putting a brake on galactic growth. In the Tadpole, however, the jets we might detect are likely faint, stubby, or disrupted. The galaxy is in a state of profound gravitational imbalance, its gas distribution chaotic from the recent collision. This unsettled environment means the black hole's fuel supply is messy and turbulent, possibly starving the jet formation mechanism or causing it to sputter and change direction. The radio emission from such a jet would be a ghostly, filamentary structure, a faint scar against the brighter background of the galaxy's star-forming regions. Detecting it requires patiently mapping the tadpole with radio telescopes, looking for that telltale linear feature aligned with the core. A confirmed jet, even a faint one, would be a direct line into the black hole's engine room, revealing the orientation of its spin and the state of its magnetic prison. It would show us that even amid the chaos of a collision, the most fundamental forces of physics are still at work, trying to impose order from the very heart of the storm. The gravitational lens is a powerful clue, but it points toward a deeper, invisible architecture. Mapping the motion of stars and gas within the tadpole's long tail reveals a subtle anomaly, a gravitational fingerprint that cannot be explained by the glowing material we see. The visible stars are moving as if tugged by an unseen hand, suggesting a hidden mass clinging to the tidal stream. This is the signature of a dark matter clump, a ghostly anchor woven into the fabric of the wreckage. Astronomers map this invisible substance not by seeing it, but by reading its influence on everything else. They measure the velocities of stars and hydrogen clouds along the tail's length with exquisite precision. If those objects are moving faster than the visible mass alone can account for, the only explanation is the gravitational pull of additional, unseen matter. It is like watching leaves swirl in a stream, their frantic motion betraying the presence of a powerful underwater current you cannot see. The significance of finding such a clump in a tidal tail is profound. Dark matter is thought to form a vast, diffuse halo around galaxies, a spherical cloud that extends far beyond the visible disk. During a galactic collision, this dark matter halo interacts with itself. Computer simulations show that while stars and gas are dramatically stretched into tidal tails, the dark matter, which does not experience friction or pressure, behaves differently. It can be stripped out as well, but often in broader, more diffuse streams. Discovering a concentrated clump within the visible tail would challenge and refine those simulations. It suggests dark matter might be more sticky or clustered within galaxies than we thought, or that the tidal forces during the collision were even more complex. This invisible knot drifting along the river of stars is a relic of the intruder dwarf galaxy's own hidden skeleton, a piece of its dark matter halo that was torn loose and now travels with the stellar debris. It confirms that the collision was not just a meeting of stars, but a violent entanglement of entire invisible ecosystems, their shadows forever cast across the light. The brilliant glare of a quasar is one of the most recognizable signatures in the cosmos, a beacon from a galaxy's core powered by a ravenous supermassive black hole. Yet here in the Tadpole, we find a master of disguise, an object shining with all the ferocious intensity of a quasar, but born from an entirely different kind of violence. This is a quasar imposter, a phenomenon that challenges everything we think we know about reading the light from distant galaxies. From 420 million light-years away, its spectrum screams power, showing the broad, energetic emission lines characteristic of matter whirling at tremendous speeds. The immediate, obvious conclusion would be a classic quasar, a black hole feasting at a galaxy's heart. But the Tadpole's unique, shattered state forces a second look. The imposter's light does not come from the calm, organized center of a mature spiral. Instead, it erupts from a frenzied knot within the tidal tail or a super-dense star cluster, a place where the physics of creation mimics the signature of destruction. The true nature of this brilliance is a cosmic puzzle. It could be an extreme starburst region on a scale we can barely comprehend. Imagine not one, but hundreds of those massive Wolf-Rayet star clusters packed into an area just a few hundred light-years across. The combined ultraviolet radiation from millions of hot, young stars and the catastrophic winds from thousands of dying giants would ionize surrounding gas to an incredible degree, producing an integrated spectrum that looks, for all intents and purposes, like that of a single, monstrous engine. Alternatively, the imposter might be hiding a more compact truth, one of those intermediate mass black hole candidates, but in a state of extreme, brief gluttony. If such a black hole at the heart of a dense cluster managed to capture and tear apart a gas-rich star or cloud, it could undergo a temporary eruption of accretion, shining with quasar-like power without being a supermassive giant. Distinguishing between these possibilities from our distant vantage point is a monumental challenge. Astronomers must become cosmic detectives looking for subtle clues in the light. They search for the faint, underlying continuum of a stellar population, which would support the starburst hypothesis. They analyze the exact width and shape of the emission lines, as gas orbiting a single, compact object has a different velocity signature than gas being churned and shocked by countless stellar winds and supernova in a cluster. Sometimes the smoking gun is the location itself, a quasar signal emerging not from the galactic core, but from a brilliant, off-center knot in the chaotic tail. The Tadpole is the perfect host for such an imposter because it is a galaxy literally in pieces, where normal rules are suspended. It concentrates the raw materials for star formation on unprecedented scales, while also creating the dense, chaotic environments where black holes of all sizes can find a sudden, spectacular feast. This object forces us to question our assumptions, reminding us that the universe often presents us with its most dazzling illusions, where the line between a billion stars being born and a single dark giant devouring everything can, for a glorious moment, appear exactly the same. Nestled within the sprawling chaos of the Tadpole's disk is a structure that seems too perfect, a faint, almost circular arc of stars. This ring fragment is an orphan chapter from a galactic story that began long before the main collision. To understand it, we must envision a different kind of cosmic accident, one with surgical precision. A classic ring galaxy, like the famous Hoag's object, forms not from a glancing blow, but from a dead-center bullseye strike. Imagine a small, dense galaxy, perhaps a dwarf, plunging directly through the heart of a larger spiral disk, perpendicular to its plane. The intruder's gravity acts like a stone dropped into a galactic pond, sending a powerful density wave rippling outward through the larger galaxy's disk. This wave compresses gas and triggers a firestorm of star formation that propagates outward, leaving a brilliant, expanding ring of young blue stars, while the galaxy's core, relatively undisturbed, sits serenely in the center. The result is a stunning cosmic bullseye, a temporary and rare structure. The fragment we see in the Tadpole is likely a surviving piece of such a ring, but from the smaller victim galaxy, not the Tadpole itself. Before the dwarf intruder we now see was torn apart, it may have itself been a ring galaxy, the product of an even older, perfectly aligned collision in its deep past. When it later approached the Tadpole for its fateful encounter, the tidal forces did not create a new ring, they shattered an existing one. The graceful, circular structure was stretched and broken, with only this single, resilient arc surviving the gravitational onslaught relatively intact, now embedded like a fossil within the larger galaxy's spiral arm. This transforms the fragment from a mere curiosity into a multi-layered historical record. It tells us that the dwarf galaxy had a complex life of its own, a history of prior mergers and collisions long before it became the tadpole's meal. Its journey was not a simple path from solitude to destruction, but a series of dramatic interactions, each leaving a mark. Finding such a fragment forces astronomers to read the tadpole's wreckage with even greater care, searching for other subtle structures that might be inherited from the intruder's own past. It is a ghostly echo within an echo, a reminder that every galaxy we see is a palimpsest with older stories written faintly beneath the most obvious violent chapters. Drifting in the profound darkness between galaxies is a phantom of pure potential, a silent cloud of hydrogen with no stars to call its own. This intergalactic gas cloud is a ghost, detectable only by the faint radio whisper of its hydrogen atoms. In visible light surveys, its location appears as an empty patch of void adjacent to the tadpole's tail. But tune a radio telescope to the specific frequency of 21 centimeters, and the cloud materializes a vast, diffuse structure of primordial gas. Its very existence is a direct consequence of the collision's violence. The immense tidal forces that stretched stars into a tail also acted like a cosmic comb, pulling and shearing tenuous gas from the outer disks of both galaxies. This particular cloud was likely ripped free entirely, flung out with enough velocity to escape the main gravitational pull, becoming an orphan in intergalactic space. Its composition is a time capsule, predominantly simple hydrogen and helium, the raw, unprocessed elements that have existed since the Big Bang, untouched by the nuclear forges inside stars. This raises a fascinating question about its destiny, a question of cosmic pressure. For a gas cloud to collapse and ignite new stars, it needs to overcome its own internal pressure and external disturbances. Typically, this requires a trigger, a shock wave from a nearby supernova or the compressive force of a spiral arm's density wave. This orphan cloud, however, floats in a near-perfect vacuum, isolated and undisturbed. Without a catalyst, its own gravity may be too weak to pull it together against even the faint thermal motions of its atoms. It could remain a dark, wandering reservoir for billions of years, a sleeping giant of unused material. Yet, its proximity to the turbulent tadpole offers another possibility. A future close pass by another tidal stream or the shock front from a powerful galactic wind could one day slam into this cloud, compressing it just enough to tip the balance. In that moment, pockets within the cloud would begin to condense, temperatures would soar, and nuclear fusion would flicker on in 1,000 points of light, transforming the phantom into a sudden, brilliant archipelago of newborn suns. For now, it is a monument to patience, a reminder that the universe often creates the ingredients long before it decides to light the fire. The faintest rivers in the tadpole are not made of gas but of stolen suns. Wrapping around the galaxy's outer halo is a delicate stellar stream, a gossamer trail of stars so diffuse it disappears into the background unless you know exactly how to look. This is not part of the bright, gaseous tail. It is something older and more subtle, the final breath of the devoured dwarf galaxy. Each star in this faint ribbon was once a loyal citizen of that smaller system, orbiting its own center. The violent gravitational tides during the collision did not just pull the dwarf apart, they unraveled it, stretching its stellar population into a long, looping arc that now orbits the tadpole like a celestial ring of smoke. These streams are the archaeological remnants of galactic cannibalism, the fossilized bones of a meal not yet fully digested. To astronomers, they are a treasure map. By meticulously charting the positions, colors, and motions of stars in this stream, they can perform a kind of cosmic forensics, tracing the ghostly path back to its origin. The stream's curvature reveals the exact orbit the Dwarf galaxy took as it was consumed. The mix of star types within it, the ratio of old red stars to younger blue ones, tells us about the Dwarf's original structure and its history of star formation before the catastrophe. Was it a small, puffy, irregular galaxy or a denser, more structured dwarf spheroidal? The stream holds the answer. This faint river is more than a monument, it is a recording device. As the stream continues to orbit, it will eventually phase mix, its stars dispersing so completely they become indistinguishable from the tadpole's own halo. But for now, this fading signature allows us to watch a merger in its final, graceful act, a slow-motion dissolution written in a million points of ancient light. That faint stellar stream is a record of ancient theft, but some stolen treasures shine with a light all their own. Among the millions of stars swept into the tadpole's chaos, one particular point of light burns with a deep, somber crimson. This is not the blue-white fire of a newborn or the steady yellow of a middle-aged sun like our own. This is the glow of a cosmic ember, an unusually red supergiant. It is so distinct and so vividly colored that astronomers can pick it out as an individual star even across 420 million light-years, a testament to its sheer monstrous scale. We are looking at a star in its final act, a swollen giant that has exhausted the hydrogen fuel in its core. In response, its core has contracted and grown hotter, beginning to fuse helium into carbon and oxygen. This new, fiercer furnace pumps out enormous energy, causing the star's outer layers to expand to a truly absurd degree. The star becomes a bloated, tenuous sphere of relatively cool gas. To grasp its size, place this star at the center of our own solar system. Its searing surface would not stop at the orbit of Earth or even Mars. It would stretch out nearly 500 million miles from its core, swallowing the inner planets whole and extending its crimson atmosphere all the way to the orbit of Jupiter. The entire inner solar system would exist inside this star, a concept that bends the mind. Its redness is a direct clue to its temperature. While our yellow sun has a surface temperature around 10,000 degrees Fahrenheit, this supergiant's outer layers have cooled to perhaps half that, glowing with the deep red hue of a dying campfire. But this peaceful, expansive phase is a brilliant illusion, a calm before the most violent storm a star can muster. Its immense size is a symptom of profound internal instability. Deep within its core, a countdown is ticking. It is now forging heavier and heavier elements, building up a central iron ash that cannot be fused to release energy. When that iron core grows too large, perhaps in a matter of mere thousands of years, the entire gravitational architecture of the star will catastrophically fail. It will collapse in upon itself in less than a second, then rebound in a titanic shockwave that rips the star apart from the inside out. The light from that supernova explosion will, for a few glorious weeks, outshine the entire Tadpole Galaxy. This single, resolved red dot is therefore a prophecy written in fire, a star we can name and watch, knowing its spectacular end is written in the laws of physics. It is a reminder that within the grand, slow-motion collision of galaxies, there are countless individual dramas of life and death, each playing out on a scale that dwarfs our entire world. That deep crimson prophecy of a supergiant's end points toward an even more extreme fate. Hidden within the archival light of the tadpole could be the ghost of the universe's ultimate detonation, a gamma-ray burst afterglow sight. This is not an object you can point to in a single image. It is a cosmic crime scene identified by piecing together clues across time and wavelength. Gamma-ray bursts are the single most powerful explosions known. brief flashes of gamma radiation so intense they can outshine, for a few seconds, every other source of gamma rays in the cosmos combined. They come in two primary flavors. Long bursts lasting more than 2 seconds are thought to be the death cries of the most massive stars, resulting in a hypernova that produces a narrow, relativistic jet pointed directly at Earth. Short bursts lasting less than 2 seconds are the suspected product of a different cataclysm, the merger of two ultra-dense stellar corpses, like neutron stars or a neutron star and a black hole. When these objects finally spiral together after billions of years in a decaying orbit, they collide in a kilonova event, spraying heavy elements like gold and platinum into space and for a split second, focusing unimaginable energy into twin beams. If one of those beams was ever pointed at our telescopes from within the tadpole, even 420 million years ago, its fleeting signal would have been recorded. The evidence today would be subtle. After the initial gamma-ray flash fades in seconds, it leaves behind a fading afterglow across other wavelengths, from X-rays to visible light to radio, as the jet slams into the surrounding interstellar material and decelerates. Astronomers comb through old satellite data, looking for a brief, intense spike of gamma rays whose coordinates align with the tadpole. They then search deeper optical and infrared images of that exact spot, hunting for a faint, fading patch of light that does not belong to a star or nebula, or better yet, the faint, expanding remnant of the associated kilonova. Finding such a sight would be like discovering the cooled ashes of a cosmic fire that burned brighter than a billion suns, but only for the blink of an eye. It would tell us that within the chaos of the tadpole, the most violent possible stellar endings have already occurred, seeding its gas with precious metals forged in the heart of a neutron star collision, and proving that this galaxy has been a theater for the full spectrum of cosmic violence. The universe's most powerful magnetic fields are not found in laboratories, but in the corpses of stars. Within one of those faint, expanding supernova shells we discussed earlier, a different kind of stellar corpse might be spinning in silence. This is not an ordinary neutron star. It is a potential magnetar, a cosmic magnet of almost inconceivable power. Born in the most violent supernova, a magnetar is a neutron star that took a special, terrifying turn. All neutron stars are dense, a sun's worth of mass crushed into a sphere the size of a city, so dense that a sugar cube-sized piece would weigh as much as a mountain. But a magnetar's magnetic field is its defining, monstrous feature. While a typical neutron star has a magnetic field 1 trillion times stronger than Earth's, a magnetar's field is another 1,000 times stronger still. To grasp that scale, imagine a magnet so powerful that if one were located halfway between the Earth and the Moon, it would erase the data from every credit card on our planet. This field is not a passive trait, it is an active, destructive force. It stresses the neutron star's rigid crust, a crust made of iron nuclei locked in a crystalline lattice 10 billion times stronger than steel. Even this unimaginably strong material cannot withstand the magnetar's internal tension forever. Periodically, the crust cracks. These are starquakes, seismic events on a stellar scale that release more energy than 1,000,000 magnitude 10 earthquakes. Each crack causes a catastrophic rearrangement of the magnetic field lines anchored to the star's surface. This sudden shift unleashes a storm of high-energy radiation, a blinding burst of X-rays and gamma rays that can briefly outshine the entire Milky Way galaxy. For a few tenths of a second, the magnetar becomes the brightest object in its region of space, a flash of pure magnetic fury. Yet in the tadpole, such a beast might be hiding in plain sight, disguised by its own slow spin. Most neutron stars we detect are pulsars, lighthouses that sweep beams of radiation past Earth with incredible regularity as they spin, sometimes hundreds of times per second. A magnetar, however, often spins much more slowly, perhaps once every 10 seconds. Its beam of radiation might simply never point toward Earth, or its magnetic field might be so twisted that it does not produce a clean, pulsing signal we can easily recognize. We would only know it by its violent outbursts or by the persistent, high-energy glow of its magnetic field slowly cooking the surrounding supernova remnant. Finding one here would mean that within a bubble of expanding debris, a silent, spinning vault contains a force that bends the very rules of matter and energy, a dormant dragon waiting for its next world-shaking tremor. While Magnetars represent one extreme of stellar death, another violent partnership unfolds across the Tadpole. A tight binary star system locks two objects in a gravitational embrace so close that their fates are permanently entwined. This is no peaceful orbital dance. It is a cosmic vampirism where one star, a dense stellar corpse, slowly consumes the lifeblood of its living companion. The participants define the drama. The vampire could be a white dwarf, the Earth-sized core of a sun-like star, a neutron star, or even a stellar mass black hole. The donor is often a more normal star, like a red giant or a main sequence star, swollen and vulnerable as it ages. Their orbits are measured in hours, not years, bringing them so close that the intense gravity of the dense corpse stretches the atmosphere of the companion star. It pulls a stream of hydrogen gas directly from its partner, a river of stolen material that spirals inward, but this gas does not fall straight down. Conservation of angular momentum, the same physics that keeps a spinning ice skater upright, forces the infalling gas to form a whirling, flattened disk around the denser object, a searingly hot accretion disk. The phenomena born from this disk are spectacular and varied. If the vampire is a white dwarf, the stolen hydrogen piles up on its incredibly dense, hot surface. Over time, the pressure and temperature at the base of this hydrogen layer becomes so extreme that it triggers runaway nuclear fusion, like lighting a match on a pile of gunpowder. The entire accumulated layer detonates in a titanic thermonuclear explosion. From our distant vantage point, we see this as a nova, a sudden, dramatic brightening of the star by tens of thousands of times, a new star appearing in the galaxy for a few weeks before fading back to obscurity. This is not a destructive event for the white dwarf. It survives, and the cycle of theft and explosion can repeat every few decades or centuries. If the accreting object is a neutron star or black hole, the physics grows even more extreme. The gas in the disk, spiraling inward at nearly the speed of light, is heated by immense friction to temperatures of millions of degrees. It glows not in visible light, but in high-energy X-rays, turning the binary into one of those brilliant, pinpoint X-ray sources we can detect across intergalactic space. The variability of these systems is utterly unpredictable, a flickering dictated by the chaotic flow of material from donor to disk. Clumps of gas might fall in sudden torrents, causing the X-ray output to flare wildly for hours before settling back into a faint hum. The donor star itself might pulse or experience its own instabilities, altering the rate of the theft. Watching such a system is like watching a hungry predator and its prey locked in a cage, their struggle playing out in a frantic, high-energy light show that never follows the same script twice. While binary systems steal from the living, other stellar societies preserve the chemistry of a much older theft. Orbiting the fringes of the Tadpole is a dense, ancient sphere of stars, a globular cluster that should be a predictable relic. These clusters are typically the oldest structures in a galaxy, formed from the pristine hydrogen and helium of the early universe, before many generations of stars had cooked heavier elements. Their stars are therefore metal-poor, meaning they contain very low amounts of elements heavier than helium. This particular cluster, however, holds a chemical secret. When astronomers analyze its starlight, they find an anomalous metallicity. Its stars are not as metal-poor as they should be. They contain a subtle but significant sprinkle of heavier elements like carbon, oxygen, and iron. This is a fingerprint out of place, a clue that this cluster's history is not what it seems. The anomaly points to two thrilling possibilities. The first is theft. This cluster may not have been born in the tadpole at all. Instead, it could be a trophy ripped from the heart of the intruder dwarf galaxy during the collision. If that dwarf had a more complex star-forming history than we assumed, creating and dispersing some heavier elements before the merger, its globular clusters would carry that enriched signature. The cluster's unusual chemistry would then be the inherited wealth of its original, devoured home. The second possibility is even more intriguing. This cluster might have formed in the unique, turbulent aftermath of the collision itself. Imagine the shockwaves from the galactic impact compressing not just loose gas, but also pre-existing clouds of material that had already been lightly enriched by a prior generation of stars. This would create a globular cluster that is ancient by human standards, but relatively young for its kind, born from the chaos rather than the primordial dawn. Either way, this dense ball of stars is no longer just a simple ornament. It is a fossil, a celestial time capsule with a chemical barcode that tells a story of displacement and violence. Its very presence and composition help astronomers map the flow of material during the merger, tracing which pieces came from where, and revealing that even the oldest-looking objects can hold the freshest evidence of cosmic crime. The faint afterglow of a gamma-ray burst is one kind of cosmic ghost, but the tadpole may hold another, more patient kind of echo. Centuries or even millennia ago, a star within its spiral arms reached the end of its life and exploded. For a few weeks, it shone with the light of billions of suns, a new, brilliant point visible to any hypothetical astronomers within that galaxy. That flash of light, a spherical wave of photons, raced outward at the speed of light. Most of it streamed unimpeded into the void, fading into darkness, but some of that light did not travel a straight path to us. It slammed into vast, floating walls of interstellar dust, intricate clouds of cosmic soot lingering between the stars. The light did not simply vanish. It scattered, reflecting off the dust grains like a flashlight beam hitting fog. This reflected light takes a longer, indirect route to our telescopes, arriving years or even centuries after the direct light of the explosion faded from view. What we see is a light echo, a luminous shell expanding silently through space, a perfect record of that ancient flash still traveling, still visible. It is not the supernova itself, but its ghost, a delayed broadcast of a catastrophe that is already long over. Finding such an echo in the tadpole would be like discovering a cosmic replay button. Astronomers search for them by comparing deep field images taken years apart. They look for faint, circular or arcing structures of light that are slowly growing larger, expanding away from a central point where nothing remarkable appears today. The geometry is everything. Think of the supernova's initial flash as a stone dropped in a pond. The ripples are the wave front of light. Now imagine that pond has lily pads floating at different distances from the center. The ripple hits the closest lily pad first, then a moment later a farther one. From above, you see expanding rings emanating from the center. In space, the lily pads are sheets of dust at different distances from the exploded star. We see not a continuous shell, but separate, illuminated arcs, each corresponding to a dust cloud at a specific distance. By measuring the angular expansion of these rings over time, astronomers can perform a breathtaking calculation. They can determine the precise distance to the supernova itself, a measurement independent of any other method. More hauntingly, they can triangulate the exact location in the modern galaxy where that star once lived. Now just a quiet patch of space, perhaps containing a neutron star or black hole, the invisible corpse of the event that created the echo. The scientific value is profound, but the emotional resonance is deeper. A light echo is a literal look into the past. The light now reaching our eyes from that expanding shell left the dust cloud only a few years ago, but it carries information from the supernova event centuries before that. We are not seeing the explosion as it is now, we are seeing it as it was, a delayed snapshot. By analyzing the spectrum of the echo breaking its light into colors, we can study the chemistry and physics of that ancient explosion with modern instruments long after the fireball itself has vanished. We could determine what type of star died, what elements it forged in its final moments, and how asymmetrical the blast might have been. It turns the tadpole into a museum with a living exhibit where the light from a single catastrophic moment is still bouncing through the halls, allowing us to study an event we missed by generations of cosmic time. It begs a quiet question. If we could see the light echoes from all its ancient cataclysms, what symphony of past violence would be ringing through the tadpole's spiral arms right now? Deep within one of those turbulent, dusty clouds, where the infrared blobs glow with hidden heat, a different kind of signal whispers its presence. This is a natural maser, a cosmic microwave laser born from the chaos of stellar birth. The word maser stands for microwave amplification by stimulated emission of radiation, and it describes a process where molecules trapped in an energized state are triggered to release their energy in perfect sync, producing an intense, focused beam of radio waves. Unlike the broad, noisy radio emission from hot gas, a maser beam is a pure, narrow-frequency signal, a single, powerful note in the cosmic static. In the tadpole, astronomers pinpoint these signals to specific hyperactive nurseries. The most common masers involve water or methanol molecules. Picture a dense, swirling disk of gas and dust collapsing to form a massive protostar. As material spirals inward, it creates immense shock waves and is bathed in intense radiation from the newborn star. This energizes the molecules, pumping them up like billions of tiny springs. When a passing radio wave of just the right frequency tickles one of these excited molecules, it causes it to release its stored energy as an identical radio wave. That new wave then triggers another molecule and another, creating a cascading, amplified chain reaction that results in a brilliant, coherent beam shooting out from the cloud. We detect this as an incredibly bright, pinpoint radio source, a lighthouse beacon that marks the exact location of a massive star fighting its way out of its dusty cocoon. But these masers are far more than just brilliant markers. They are some of the most precise tools in the astronomer's kit. Because the beam is so pure and narrow, its frequency can be measured with exquisite accuracy. Any motion of the gas cloud along our line of sight will Doppler shift that frequency, just like the changing pitch of a passing siren. By tracking this shift over time, astronomers can map the internal motions within these star-forming regions with a precision of just a few kilometers per second, watching gas whirl in accretion disks or blast outward in protostellar jets. Even more powerfully, if a maser source is part of a rotating disk, we can use its motion to perform direct geometry. By observing masers on one side of the disk moving toward us and those on the other side moving away, we can calculate the disk's physical size and its distance from us through simple trigonometry. This turns a faint whisper of excited molecules into a celestial ruler, allowing us to measure vast distances across the universe with remarkable confidence. That single, amplified point of radio light is therefore both a signpost of violent creation and a calibration point for mapping the cosmos itself. Those natural masers pinpoint the cradles of stellar giants, but the collective breath of such giants can hollow out cavities on a truly galactic scale. Scattered across the tadpole's spiral arms are immense, bubble-like structures in the interstellar gas, some spanning hundreds of light-years from rim to rim. These are supershells, the largest coherent structures an individual galaxy can produce, and they are monuments to the power of stellar societies. A single supernova remnant might be 10 light-years wide, but a supershell is an order of magnitude larger, a cavern carved not by one explosion, but by the sustained, coordinated fury of an entire stellar association. Imagine a bustling metropolis of massive stars, dozens of luminous blue variables and Wolf-Rayet stars, all born from the same giant molecular cloud roughly at the same time. Each one of these stars, throughout its short, violent life, blasts its surroundings with a ferocious stellar wind, a continuous supersonic gale of charged particles. Then, one by one, they die. Over a span of a few million years, these stars reach the end of their fuel and explode as supernova, each detonation sending a powerful shockwave racing through space. The physics is one of compounding violence. The winds from the living stars first blow a large but relatively fragile bubble in the surrounding gas. When the first supernova erupts, its shockwave slams into the walls of that wind-blown bubble, energizing it and driving it outward faster and farther. Then another star explodes and another, each successive shockwave piling energy into the expanding shell like a series of hammer blows on the same nail. The result is a single gargantuan structure, a supershell whose walls are made of swept-up, compressed interstellar material glowing in the soft light of ionized hydrogen. They are often not perfect spheres, but vast, irregular chimneys and arcs, their shapes distorted by the density of the surrounding galactic disk and the uneven timing of the stellar deaths within. Finding these in the tadpole is a direct observation of stellar feedback operating at its most extreme. This is how stars, especially massive ones, talk back to their galaxy. They do not simply form and die in isolation. Their combined energy input physically reshapes their environment on scales that are almost unimaginable. A single supershell can clear out an entire region of a spiral arm, evacuating gas and shutting down star formation within its hollow interior for eons. Yet, in a beautiful paradox, it also triggers new creation. As the supershell's dense, cool outer rim expands and destabilizes, it can fragment under its own gravity, collapsing into new clusters of stars along its periphery. The structure becomes a self-propagating ring of fire, where one generation of massive stars literally blows the bubble that sets the stage for the next generation to form around its edges. In the tadpole, a galaxy already defined by collision and chaos, these supershells are the fingerprints of localized, internally generated pandemonium. They are the clearest sign that within the grand wreckage of the merger, smaller, equally violent stories of stellar life and death are constantly unfolding, each one leaving a lasting imprint on the galactic landscape. But that chemical fingerprint is not the only anomaly a stolen cluster might carry. Among the brilliant beads of newborn dwarf galaxies in the tadpole's tail, one particular knot of blue fire stands out for a different, more ghostly reason. It shines with the fierce light of young stars, yet the motion of those stars tells a heavier story. They whirl within their tiny island universe with a velocity that defies the visible mass. The math is inescapable. There is more gravity here than the glowing gas and newborn suns can possibly account for. This suggests a profound and puzzling possibility that this tidal dwarf galaxy, forged from the wreckage of a collision, may already be wrapping itself in its own cloak of dark matter. This is a direct challenge to one of astronomy's long-held expectations. Classic tidal dwarf galaxies, born from the stripped gas and stars of a larger collision, were thought to be pristine in a specific way. They were expected to be almost devoid of dark matter. The reasoning was elegant. Dark matter halos are vast, spherical, and diffuse. During a galactic collision, the visible stars and gas, which are concentrated in the disks, feel strong tidal forces and friction, getting pulled out into spectacular tails. The dark matter, however, behaves more like a swarm of ghosts passing through itself without colliding. Simulations suggested it would not be pulled out into the same fine, dense streams as the baryonic matter, the normal stuff we see. Therefore, any dwarf galaxy condensing from that tidal stream should be made almost purely from that normal stuff, a galaxy of luminous matter with little dark scaffolding. The anomalous motions in this particular tadpole dwarf throw a wrench into that clean theory. If the measurements hold, it implies one of two thrilling scenarios. The first is inheritance. Perhaps this knot of gas did not form from perfectly stripped material alone. It might have captured or been born around a pre-existing clump of dark matter that was itself torn from the halo of the intruder dwarf galaxy during the chaos. This would mean the dark matter halos of galaxies are not perfectly smooth, but contain substructure, lumps and knots that can be harvested by tidal forces. The second possibility is even more radical, that dark matter is not entirely collisionless. Some exotic theoretical models suggest dark matter particles might have a tiny ability to interact with each other beyond gravity. If that were true, they could experience a form of drag or friction during a collision, causing them to be pulled out into the tidal streams alongside the gas, becoming available to seed new dwarf galaxies. Either way, the consequence is the same. We would be looking at a newborn galaxy that, against all odds, brought its own shadow into the world, confirming this is a painstaking task. Astronomers must map the rotation of this tiny, distant object with extreme precision, using the Doppler shift of its light to chart how fast stars are moving at different distances from its center. They then construct a model, calculating how much mass must be present to keep those stars in their orbits. The difference between that total mass and the mass they can see in stars and gas is the dark matter contribution. It is a measurement at the very edge of our technical ability, a whisper of gravity pulled from a faint smudge of light 420 million light-years away. Yet, if true, it reshapes our understanding of both galaxy formation and the nature of dark matter itself. It suggests the universe's hidden skeleton is more intimately entwined with the luminous bodies we see, and that even in the aftermath of violence, the first thing to coalesce in a new island universe might not be stars but an invisible gravitational embrace. What other fundamental rules might be written in the faint motions of these celestial newborns? Suspended in the profound emptiness between the tadpole's head and tail is a tiny, isolated island of light. This compact star cluster is a true cosmic orphan, adrift in the intergalactic void with no visible parent galaxy or nebulous cradle. It shines with the collective light of perhaps 100,000 stars, bound together by their mutual gravity into a dense spherical swarm. Yet its location makes no sense. It is too far from the main body to be a typical halo cluster, and it does not lie within the glowing river of the tail. It simply hangs there, a glittering pendant in the dark, and its very existence forces a difficult question. How did a family of stars this large end up so completely alone? The debate over its origin is a classic cosmic mystery, a choice between two equally dramatic stories. The first is a tale of violent ejection. During the peak of the galactic collision, the gravitational chaos could have acted like a cosmic slingshot. A star cluster orbiting within the intruder dwarf galaxy, or perhaps one newly born in the turbulent disk of the tadpole itself, could have received a tremendous gravitational kick. Picture the cluster as a stone in a sling, swung faster and faster by the passing galaxies until it was flung free entirely, launched with enough velocity to escape the galactic pull forever. It would have sailed out into the intergalactic medium, leaving its home behind to become a permanent wanderer. The second story is one of improbable, solitary creation. Perhaps a lone, massive cloud of gas was itself stripped from the galaxies during the collision. Drifting in the quiet darkness, far from the triggering shockwaves of the main event, this cloud eventually succumbed to its own gravity. It collapsed in upon itself, and in that isolated void ignited a single, brilliant burst of star formation. The cluster was born in place, an only child with no siblings and no mother galaxy, a stellar society that formed in the ultimate quiet of deep space. Distinguishing between these origins requires stellar detective work. Astronomers analyze the cluster's color and the specific signatures in its starlight. If its stars are uniformly old and red, it likely formed long ago and was ejected, a veteran of the collision. If it shows a population of hot blue stars, it points to a more recent, in situ birth from that lone gas cloud. Its chemical makeup is another clue. a fingerprint that might match the metal-rich disk of the Tadpole or the more pristine halo of the devoured Dwarf. This orphan cluster is more than a curiosity. It is a test of our understanding of gravity's reach and star formation's limits. Can a galaxy's gravitational fury truly punt an entire city of stars into the abyss? And can the quiet, cold space between galaxies ever become a nursery? This tiny, distant smudge of light holds the answer, a silent testament to the fact that in a universe of collisions, some things are not just broken but thrown clear into the darkness. A nebula near the Tadpole's heart refuses to hold a single shape. This variable nebula is a cosmic chameleon, its luminous tendrils shifting in brightness and form over months and years, as if the ghostly cloud itself is breathing. The phenomenon is an illusion of shadow and light on a staggering scale. At its core lies not a steady beacon, but a variable star, one that pulses in brightness with its own unstable rhythm. This star is the lighthouse, and the surrounding nebula is the dense, interstellar fogbank it illuminates. The star's intense radiation causes the gas to fluoresce, but the view from our distant vantage point is never the same twice. Dense, dark knots of dust and debris orbit the star, casting immense, light-year-long shadows across the nebula's structure. As these clouds drift, they block our view of different glowing regions, making some filaments seem to fade while others suddenly brighten into view. It is a celestial puppet show where the puppeteers are clumps of cosmic soot, and the stage is light years across. The most famous example in our own galaxy is Hubble's Variable Nebula, a fan of light that changes visibly in telescope images over just a few decades. The one in the Tadpole operates on the same principle, but across a far more immense distance. Its changes detectable only through meticulous, long-term observation. Watching it is an exercise in cosmic patience, revealing that even seemingly permanent structures in the galaxy are engaged in a slow, graceful dance, their appearance dictated by the silent drift of shadows we can never directly see. Even the emptiest spaces near the Tadpole are not truly empty. A vast, diffuse cloud of hydrogen, moving at hundreds of kilometers per second, is on a collision course with the galaxy's most delicate structure. This high-velocity cloud is a ghost from the collision's aftermath, or perhaps a wanderer from the true intergalactic void, now destined to slam directly into the stellar river of the tail. The impending impact is a slow-motion catastrophe of breathtaking scale. The cloud itself is likely millions of times the mass of our Sun, yet so thinly spread that a handful of its atoms in a volume the size of a house would qualify as a dense crowd. It is this very tenuousness that makes the coming collision so consequential. As this massive but diffuse object plows into the slightly denser material of the tidal tail, it does not strike like a bullet but like a titanic, soft hammer. The interface between the two gas streams becomes a frontier of pure physics. Where they meet, atoms cannot simply pass through one another, they collide. These microscopic crashes translate upward in scale, creating a wall of superheated plasma, a shock front that races ahead of the cloud like the bow wave of a ship. This shock wave is the real actor, a traveling zone of immense pressure and temperature that compresses everything in its path. For the gas already in the tail, this is a transformative trigger. Imagine a quiet, slowly undulating sea of gas, where gravity is still quietly gathering material for stars over millions of years. Suddenly, a tsunami of pressure sweeps through. That gentle, ongoing collapse is violently accelerated. Pockets of gas that were on the verge of star formation are squeezed past their breaking point, while new, unstable knots are forged from previously calm material. The result, downstream from the collision front, could be a sudden, brilliant sparkle of new star clusters igniting along a segment of the tail, a localized firestorm of birth prompted by an external hammer blow. This high-velocity cloud is therefore a delayed catalyst, a secondary event that writes a new chapter of creation onto the fossilized record of the first collision. It proves that the tadpole story did not end when the galaxies finished their dance. The wreckage they left behind remains a dynamic arena, where even the faintest ghosts from the void can return to stir the embers back into flame. A stellar heart can be replaced by something far denser than fusion's fire. Among the tadpole's population of swollen red giants, one might hide a secret at its core that defies conventional stellar physics. This is a candidate Thorn-Zitkow object, a theoretical hybrid so strange it sounds like science fiction, a red supergiant with a neutron star beating in its center instead of a traditional stellar core. Picture the aftermath of a close binary system where one star has already died in a supernova, leaving behind its ultra-dense neutron star corpse. Normally, such a pair would either drift apart or, if close enough, become an X-ray binary. But in a specific, slow-motion catastrophe, the orbits can decay until the neutron star spirals directly into the outer layers of its expanding giant companion. It does not collide in a flash, it plunges inward, sinking through the tenuous outer atmosphere of the giant like a stone falling through thick fog, all the way down to the very center. There, it displaces the giant's own fusion core. The result is a stellar chimera, a vast, cool envelope of hydrogen and helium 100 million miles across, powered not by its own central fusion, but by the immense gravitational energy released as matter from the giant's innards rains down onto the surface of the neutron star at its heart. This accretion onto the neutron star creates temperatures and pressures that drive unusual nuclear reactions in a shell surrounding it. The predicted chemical signature of such an object is its most telltale clue. The unique environment around the neutron star core is thought to produce an overabundance of specific heavy elements like rubidium, lithium, and molybdenum, elements that are normally rare in the atmospheres of classic red supergiants. Astronomers hunting for a Thorn-Zitkow object would analyze the spectrum of a suspiciously red star, looking for these unusual chemical lines shining through its cool outer layers. The violent, dynamic environment of the Tadpole Galaxy makes it a prime hunting ground for such a stellar oddity. The galaxy is packed with dense star clusters where tight binary systems are common, and the gravitational shocks of the galactic collision could easily destabilize ancient orbits, triggering the inspiral needed to create this hybrid. Finding one would be a monumental discovery, confirming a 40-year-old theoretical prediction and revealing an entirely new way for stars to live and die. It would be a direct observation of stellar cannibalism and rebirth, where the corpse of one star becomes the engine for another, creating a temporary, brilliant, and profoundly strange beacon in the cosmic chaos. That stellar chimera is a monument to internal strangeness, but the tadpole also offers a window into the universe's fiery infancy. Among its many brilliant knots is a tiny, emerald spark, a compact region of star formation glowing with an unusual and vivid greenish hue. This is not a trick of the light our eyes would see, but a specific signature revealed through the colored filters astronomers use to dissect starlight. The intense green color comes from a torrent of light emitted by doubly ionized oxygen atoms, a specific fingerprint of extreme energy. Within this tiny, ferociously bright region, star birth is not just happening, it is exploding at a rate that defies the calm order of a typical spiral galaxy. Thousands of massive hot stars are screaming into existence in a volume of space that might be only a few thousand light years across, cramming the stellar output of an entire galaxy into a space smaller than our own Milky Way's central bulge. The environment is pure, unadulterated chaos where supernovae detonate in rapid succession and stellar winds blast the surrounding gas into a frenzy. It is this violence that creates the green signature. The ultraviolet radiation from all those newborn stars is so intense it strips electrons from oxygen atoms in the surrounding nebula, not once but twice. When these battered atoms recapture electrons, they release that pent-up energy as a specific shade of green light. painting the entire region in this eerie, energetic glow. This tiny green spark in the tadpole is far more than a local oddity. It is a direct analog to some of the most important galaxies in the early cosmos, objects nicknamed green pea galaxies. These were first identified not by professional astronomers, but by citizen scientists poring over data from the Sloan Digital Sky Survey, picking out small, round, and unmistakably green dots. Those distant peas are time machines, snapshots of the universe when it was only 2 or 3 billion years old, a period of rampant, chaotic star formation. They are thought to be the building blocks of the massive galaxies we see today, undergoing their first furious bursts of creation. Studying them directly, however, is incredibly difficult due to their vast distance and faintness. Their light is stretched and diluted by billions of years of cosmic expansion. This is what makes the tadpole's analog so precious. We have, by a stroke of cosmic luck, a nearby example of the same physical process. It is a local laboratory for studying primordial starbursts. Here, we can examine the mechanics of such extreme star formation with a clarity impossible for its distant cousins. We can resolve individual star clusters within the green knot, measure the velocities of its gas with precision, and directly sample the chemical makeup of its raw materials. Is the gas pristine as it was in the early universe, or has it already been enriched by prior generations of stars? The answer helps us understand if green peas were truly the first major starbursts in a region, or if they too were built on earlier, fainter generations. By dissecting this brilliant green ember in the tadpole, we are effectively running a diagnostic on the universe's childhood, understanding the conditions that govern the birth of the very first galactic structures. It is a profound connection, linking the ongoing wreckage of a modern collision to the foundational fires of cosmic dawn. What other primordial echoes might be hidden within this galaxy's shattered spiral arms? The brilliant chaos of the tadpole's spiral arms gives way to a deceptive calm at its very heart. Here, in the galaxy's central region, a curious illusion plays out across the light years. Under certain wavelengths or at specific resolutions, the core does not present a single, unified beacon. Instead, it seems to split, revealing what looks like two distinct, bright centers glowing side by side in the galactic night. This is the double nucleus illusion, a trick of perspective and cosmic architecture that forces astronomers to question what they are truly seeing. At first glance, the implications are staggering. Could this be evidence of a second supermassive black hole, a relic from the devoured Dwarf galaxy now orbiting the primary beast in a slow, decaying dance? Such a binary black hole system would be the ultimate prize, a direct confirmation that galaxy mergers funnel their central monsters together, setting the stage for a gravitational wave crescendo billions of years in the future. The alternative is a truly dual core, a sign that the merger is not yet complete, that the intruder galaxy's own central bulge of stars has survived the initial passage and now orbits intact within the larger galaxy's grip, a swallowed but not yet digested heart. Both scenarios would rewrite our understanding of the collision stage and its ultimate fate. Yet the universe is a master of sleight of hand. The most likely explanation is far more subtle, a cosmic mirage created by the very wreckage of the collision. Thick, obscuring dust lanes, twisted and concentrated by the merger's turbulence, can snake across our line of sight to the true, single nucleus. Where the dust parts, it creates windows, allowing the fierce light of the central star clusters and the active galactic nucleus to blaze through in two seemingly separate locations. Alternatively, a chance alignment could be at play. A phenomenally dense and bright star cluster, one of those blue knots born from the collision's shockwaves, could have formed on an orbit that, from our vantage point, places it directly in front of or behind the true galactic center. Its combined light, superimposed on the core's glow, would create the perfect impression of a twin. Disentangling this illusion requires the sharpest eyes in astronomy. Observations must move from broad surveys to targeted, high-resolution scrutiny. Instruments like the Hubble Space Telescope and especially adaptive optics systems on ground-based telescopes that correct for atmospheric blurring are essential. They peer into the core, not just capturing light but resolving structure. Astronomers search for the telltale signs of a single, unifying gravitational field, the specific, rapid motion of stars and gas that would orbit a single, immense mass. They map the dust distribution in exquisite detail, looking for that obscuring lane. They analyze the light from each apparent nucleus. If both sources show the broad emission lines and high-energy signatures of an active black hole, the case for a true binary grows strong. If one appears as a calm, old population of stars and the other as a frenzied mix of young stars and ionized gas, the illusion of a chance alignment becomes the leading theory. This careful forensic work does more than solve a puzzle. It teaches us a fundamental lesson in cosmic humility. The most dramatic interpretations of what we see in the distant universe are often tempered by simpler, yet equally fascinating astrophysical realities. Whether the tadpole's heart holds one monster or two, the journey to find out reveals the intricate layers of deception and truth woven into the fabric of a colliding galaxy. The galaxy's ecology depends on these titanic exhalations, and in one turbulent region, the cycle is accelerating toward a climax. Multiple supershells, those vast cavities blown by generations of massive stars, are not sitting in isolation. Their expanding walls are on a collision course with each other, and where they meet, something even more monumental is being forged. We are witnessing the impending birth of a superbubble, a cavity so immense it will break through the galactic disk entirely, venting hot, metal-rich gas into the halo above. The process begins with proximity. Imagine 3 or 4 of those colossal bubbles, each 100 light-years wide, born from different stellar associations within the same spiral arm. For millions of years, they have grown steadily, their shockwaves sweeping up interstellar material like cosmic snowplows. Now, their leading edges are only a few dozen light-years apart. The thin, pressurized gas between them is being squeezed from all sides, heated to temperatures that make it glow in X-rays. The moment of connection is not a gentle merging, it is a violent reunion. When the shock fronts finally touch, they do not simply stop. They pass through one another, interacting in complex, turbulent ways. The energy does not vanish, it redirects. The merged structure now has a new shape, no longer a set of separate spheres, but a single, irregular chamber with multiple powerful energy sources still pumping from within. The remaining massive stars and ongoing supernova at the hearts of the original shells. This combined cavity experiences a sudden and dramatic loss of pressure on one side, the side facing away from the galactic plane. The thick disk of the tadpole, with its weight of gas and dust, confines the bubble's expansion downward and sideways. But upward, toward the galactic halo, the resistance is far weaker. The hot, high-pressure gas inside the fledgling superbubble finds its path of least resistance. It begins to blow out, accelerating a fountain of million-degree plasma up and out of the disk. This is galactic ventilation on a grand scale. The fountain will rise for thousands of light-years, carrying with it the chemically enriched ashes of all the dead stars that powered the original shell's iron, oxygen, silicon, and carbon. Eventually, this hot metal rain will cool, condense, and fall back onto the disk in a vast cycle, seeding future generations of stars and planets with the elements for rocky worlds and potentially life. The region where this is about to happen in the tadpole is a pressure cooker, a visible testament to the fact that galaxies are not static islands but breathing, churning ecosystems. The combined light from the compressed gas between the shells is a prelude, a last brilliant glow before the dam breaks and the galaxy exhales a part of its soul into the void. How many such breaths has the tadpole taken over its long, violent life? A final breath can be as beautiful as it is lopsided. drifting among the tadpole's older stellar populations is a delicate, glowing veil, the last testament of a star that was once very much like our own Sun. This is an asymmetric planetary nebula, a cosmic butterfly with one wing forever clipped. The name itself is a beautiful misnomer, a relic from early astronomy when their round, greenish shapes resembled the disks of distant planets like Uranus. But this one is no perfect sphere or even a symmetrical hourglass. Its form is twisted, a luminous knot of gas on one side trailing off into a faint, extended streamer on the other, as if the dying star coughed its final breath into a strong, unseen wind. The creation of any planetary nebula is a slow, elegant unraveling. A star like our Sun, having burned steadily for billions of years, finally exhausts the hydrogen fuel in its core. It swells into a red giant, then in a series of unstable pulses, gently shrugs off its outer layers. The exposed, searing hot core, now a white dwarf, bathes this expanding shell of stellar material in intense ultraviolet radiation, causing it to fluoresce in gorgeous greens, reds, and blues. Normally, if the star were alone and calm, this ejection would be relatively even, creating a round or gently elliptical bubble. But asymmetry is a signature of drama. The bizarre, lopsided shape of this particular nebula is a fossilized record of a hidden struggle at the moment of death. One compelling suspect is a binary companion. Imagine the dying star in its expansive red giant phase, having a smaller stellar partner in a close orbit. As the giant puffs away its atmosphere, the companion star orbits within this tenuous envelope, its gravity stirring the pot like a spoon in thick soup. This interaction can funnel the outflow into two opposing jets or lobes, but if the companion's orbit is eccentric or if the mass loss is uneven, one jet can become dominant, resulting in the strikingly lopsided shape we see. Another sculptor could be the star's own, immensely powerful magnetic field. As the star contracts to become a white dwarf, its magnetic field can be amplified and twisted, channeling the ejected gas along its poles like iron filings aligning to a magnet, creating irregular, collimated outflows rather than a smooth, spherical shell. Finally, the nebula might not be fighting an internal battle, but an external one. As it expands at a gentle few tens of kilometers per second, it is moving through the interstellar medium of the tadpole. If it encounters a region of slightly denser gas or a faint, pre-existing magnetic field on one side, that side of the nebula will slow and compress, while the opposite side expands freely into the void, creating a cometary, one-sided appearance. This delicate object, therefore, is far more than a pretty grave. It is a forensic snapshot. By mapping its intricate structure and measuring the velocities of its different filaments, astronomers can work backward to diagnose the precise conditions of its star's death. Was there a secret companion? How strong was the magnetic field in the star's final moments? What is the density and flow of the invisible interstellar sea it now sails through? In its graceful, imperfect form, this asymmetric nebula holds the answers, a reminder that even the most serene-looking ends can be shaped by unseen forces, leaving a beautiful, crooked signature in the light. The universe's most fleeting and powerful radio whispers might have a home in this chaos. Fast radio bursts are the cosmos's most enigmatic signals, blasts of radio waves that pack more energy than our Sun emits in 80 years into a pulse lasting just milliseconds. They arrive from deep space far beyond our galaxy, their origins a puzzle that has taunted astronomers for years. While no fast radio burst has been definitively linked to the tadpole, its turbulent environment presents a perfect candidate factory for one specific rare class, the repeater. Most bursts are one-off events, a single scream in the dark, but a handful of sources have been caught firing off multiple bursts, sometimes sporadically, sometimes in frantic clusters. This repeating behavior is the crucial clue, pointing away from cataclysmic, one-time events like merging neutron stars and toward an object that can survive its own outburst, a cosmic engine that can fire again and again. The prime suspect is a magnetar, that city-sized neutron star with a magnetic field 1,000 trillion times stronger than Earth's. In the Tadpole, with its dense star clusters and recent supernova, the conditions are ripe for creating these magnetic monsters. Imagine such a star hidden in one of the galaxy's brilliant blue knots or within a faint supernova remnant. Its crust, under unimaginable strain from the twisted magnetic field locked inside, periodically cracks. A starquake on this scale doesn't just shake the star, it violently rearranges its magnetic prison. In an instant, pent-up magnetic energy is released, accelerating particles to near light speed. This generates a blast of radio waves so intense it can be detected across intergalactic space, a flash that to our telescopes appears as a sudden, brilliant spike on a graph, a vertical line of pure energy that appears and vanishes in the time it takes to blink. If a magnetar in the Tadpole were to experience such a quake, and if its beam of radio emission happened to sweep across our line of sight, we would record a fast radio burst with a cosmic address pointing directly back to this long-tailed galaxy. The sheer power required is staggering, forcing the object to convert magnetic energy into radio waves with an efficiency that defies our best laboratories. It is a reminder that some of the universe's loudest voices speak in a language of invisible light, and they choose to shout for only the briefest moment, leaving behind a mystery that resonates across hundreds of millions of light years. A stellar mass black hole binary is a cage fight in the dark, a pair of invisible predators locked in a final, decaying orbit. Each one is a gravitational scar left by a massive star's collapse, an object so dense that within its event horizon not even light can escape. They are not the supermassive giants at galactic centers, but smaller, more numerous monsters, each weighing between perhaps 5 and 50 times the mass of our Sun. When two of them find each other, usually within the dense core of a star cluster forged in the Tadpole's collision, they begin a dance that can last for eons, a silent waltz that only ends in a flash of invisible energy. Detecting such a pair is a challenge of cosmic proportions as they emit no light of their own. Our only chance to see them is if they are not alone. If this binary system drifts through a region rich in gas, or if a third, unlucky star ventures too close, the black holes can begin to feed. They pull material from their surroundings, funneling it into searing, whirling accretion disks. The friction within these disks heats the gas to millions of degrees, causing it to blast out torrents of X-rays. From our distant vantage point, we might see a single, brilliant X-ray source, but its light would flicker with a complex, telltale rhythm. The periodic eclipses and Doppler shifts as the two black holes orbit each other would imprint a signature on that high-energy scream, a double pulse hidden within the chaos, allowing astronomers to deduce the presence of two distinct monsters sharing a meal. But many of these binaries may have already cleared their surroundings, orbiting in pristine darkness. For those, our current telescopes are blind. Their story will be written not in light, but in the ripples of space-time itself. As the two black holes circle, they lose energy by radiating gravitational waves, ripples in the fabric of the universe predicted by Einstein. This loss causes their orbits to slowly, inexorably decay. Over millions of years, they spiral closer and closer, whirling faster and faster until, in the final seconds, they complete thousands of revolutions per second. Then they merge. In a fraction of a blink, an amount of energy greater than the combined light of every star in the observable universe is released not as radiation, but as a thunderclap in the structure of reality, a gravitational wave. Observatories like LIGO and Virgo on Earth have begun to hear these chirps from mergers across the cosmos. A binary from the Tadpole Galaxy, if it merged today, would send its ripples across 420 million light-years. While its signal would be faint, future space-based observatories like the planned LISA mission could be sensitive enough to detect the longer, slower gravitational wave hum of such a binary long before it merges, listening to the low-frequency drone of their orbit for years. Finding one here would be a direct glimpse into the afterlife of the most massive stars, revealing that the tadpole's chaos doesn't just create new suns, but also forges the darkest possible partnerships, setting the stage for the universe's most silent and violent reunions. A single star flees the scene of a violent crime, a cosmic fugitive burning a brilliant blue trail across the void. This is a runaway massive star, an O-type behemoth whose light screams of youth and ferocious heat, yet it travels alone, far from the dense stellar nurseries where such giants are born. Its path is a straight line pointing directly back to one of those brilliant blue knots in the tadpole's head or tail, a cluster it once called home. Its story is one of celestial physics pushed to the breaking point, a tale of betrayal and explosive force that launched a sun on a journey with no return. The first clue is its blistering speed, clocked at hundreds of thousands of kilometers per hour. A star simply does not achieve such velocity through normal orbital motion. It must have been shot from a cannon. Astronomers have two primary suspects for the cannon's mechanism, both born from the extreme density of a young star cluster. The first is the gravitational slingshot. Imagine this massive star, already a heavyweight, in a tight binary system with another massive partner. They orbit each other in a crowded downtown of stellar traffic. A third star, perhaps an even more massive intruder, drifts too close. The complex three-body gravitational dance that follows is inherently unstable. In the chaotic exchange of momentum, the lightest of the three is often flung clear at tremendous speed. But here, the star we see fleeing is itself a titan, which means the slingshot must have been truly monumental, possibly involving the dense core of the cluster itself. The star's binary partner could have been hurled in the opposite direction or captured by the cluster's gravity, while our fugitive received a kick so powerful it broke free of the cluster's gravitational hold entirely. The second, even more dramatic story begins with a partnership that ended in a cataclysm. This star once orbited an even more massive companion, a true stellar monarch. That companion lived fast, burned through its fuel in just a few million years, and died in a core collapse supernova. A supernova is not a perfectly symmetric explosion. If even a slight asymmetry occurs, the collapsing core can receive a kick like the recoil from a gun. In a binary system, this suddenly changes everything in an instant. The supernova instantly removes a huge fraction of the system's mass. The entire star that exploded vanishes, leaving behind a neutron star or black hole that may also be kicked away. The surviving star, once held in a balanced orbit by its partner's gravity, is suddenly released. It is no longer in orbit, it is simply moving in a straight line, at the same speed it had at the moment its partner died, like a hammer released from a spinning hammer throw. This is the supernova kick scenario, where a star is not pushed but rather let go at tremendous velocity. The runaway star we see is the sole survivor, carrying with it the orbital speed of a system that no longer exists, a permanent memorial to a partnership that ended in fire. As it travels, its solitary nature shapes the space around it. Its fierce ultraviolet radiation and powerful stellar wind plow through the interstellar medium like a ship's bow wave, compressing gas ahead of it and potentially triggering star formation along its path, even as it itself races away from any chance of family. It will live its short, brilliant life in isolation, and when its time comes to die, it will explode as a supernova far from its birthplace, its elemental ashes scattered across an empty intergalactic highway. This cosmic cannonball is a frozen moment of escape, a reminder that within the crowded cities of star clusters, the gravitational streets can be mean, and the most dramatic exits happen in a flash. Nestled within one of those brilliant blue knots of star formation is a subtle, shadowy ring surrounding a single point of light. This is a debris disk around a young star, a celestial construction zone where the future is being assembled from dust and ice. From our distant vantage point, it appears as a faint, dark silhouette against the glowing nebula behind it, or perhaps as a slight, persistent dimming in the star's infrared glow, hinting at cooler material farther out. The star itself is a cosmic infant, perhaps only a few million years old, still contracting under its own gravity and shining with the fierce, hot light of youth. Around it, the leftover material from its own birth has not dissipated. Instead, it has settled into a vast, flattened disk, a swirling platter of gas, fine dust, and countless icy and rocky fragments, all orbiting the newborn sun in an orderly, circular dance. This is the raw feedstock for planets. Within that disk, microscopic particles collide and stick together, building pebbles, then rocks, then planetesimals the size of mountains. Through countless collisions and gravitational tugs, these builders will eventually coalesce into full-fledged worlds, clearing a path through the dust as they grow. What we are seeing is the very architecture of a solar system in its earliest, most fragile state. Observing such a disk in the Tadpole Galaxy is not just adding another strange object to our list, it is a profound leap in perspective. Every single planet we have ever studied, from the rocky worlds of our inner solar system to the gas giants and icy moons farther out, began its existence in a disk just like this one. They are the universal nurseries for planets, but until now, we have only ever studied them in our own galactic backyard within the Milky Way. Confirming one in the Tadpole, a galaxy 420 million light-years away, changes the scale of the question entirely. It tells us that the physical processes of planet formation are not a local oddity or a quirk of our galactic neighborhood. They are a fundamental, universal outcome of star birth, a natural and inevitable step in the life cycle of a star, as common in the long tail of a colliding galaxy as it is in the quiet spiral arms of our own. The physics of gravity, angular momentum, and accretion operate the same way here as they do there. This means the ingredients for rocky planets, for water worlds, and for the complex chemistry of life are being mixed and delivered across the universe, in galaxies of all shapes and through histories of unimaginable violence. The silent, dusty ring around that faint star is a promise written in shadow, a declaration that even amid the grand wreckage of galactic collisions, the quiet, patient work of building new worlds has already begun. The heart of a quasar's fury can be compressed into a volume smaller than a city. Deep within the tadpole's spiral arms, a stellar corpse is putting on a scaled-down version of the same spectacular show that defines a galaxy's active core. This is a microquasar, a cosmic mimic where the physics of the unimaginably vast is played out on a human, yet still terrifying scale. At its center is not a supermassive black hole weighing billions of suns, but a stellar remnant, a black hole or neutron star perhaps only 10 times the mass of our own sun. It is locked in a tight binary dance with a normal star, relentlessly stripping material from its companion. This stolen gas forms a searing accretion disk, but here the story diverges from a typical X-ray binary. In a microquasar, the system does not just glow, it erupts, somehow, through mechanisms still not fully understood. A fraction of the incredible gravitational energy is channeled and focused not into heat but into motion. The system launches two opposing, narrow jets of charged particles, accelerating them to nearly the speed of light. These jets, screaming away from the black hole or neutron star, can stretch for light years, punching out of the immediate stellar environment and into the surrounding interstellar medium. They are perfect miniature analogues of the relativistic jets that scream from supermassive black holes, just a billion times smaller in mass and scale. This makes microquasars priceless laboratories. Watching one is like having a quasar in a controlled, nearby Petri dish, where changes happen not over millions of years, but over days, weeks, or months. We can observe the entire life cycle of a jet eruption, from its initial launch to its eventual fading, in real time. By studying how the jet's power correlates with changes in the X-ray brightness from the inner accretion disk, astronomers can decode the fundamental link between how fast a black hole eats and how powerfully it can spit energy back out. These systems are nature's own particle accelerators, far more powerful than anything we can build on Earth. The turbulent magnetic fields within the jet can boost electrons to energies that make the Large Hadron Collider look like a toy, causing them to emit across the spectrum from radio waves to gamma rays. A microquasar in the tadpole is a stark reminder that the universe often repeats its most dramatic patterns at every scale, from the galactic core down to the neighborhood of a single dead star, proving that the same violent, beautiful physics is written into the fabric of reality, no matter the size of the stage. A chemical fingerprint in the tadpole's gas does not match the galaxy's expected ledger. In a specific, sprawling region, the cosmic accounting of elements is off, with oxygen, nitrogen, and iron appearing in ratios that defy the standard recipes for stellar evolution. This anomalous chemical abundance is a ghost in the spectrum, a subtle shift in the colored lines of light that reveals a history written not in stars but in their explosive deaths. To understand the strangeness, we must first know what normal looks like. In a typical, settled galaxy like our own Milky Way, elements are forged and dispersed in a predictable cycle. Massive stars live fast and die young in core collapse supernova, scattering oxygen, neon, and magnesium into the void. Slower burning sun-like stars end their lives more gently as planetary nebulae, contributing carbon and nitrogen. The very heaviest elements, like iron, require the most extreme conditions, often coming from the titanic detonations of white dwarfs or the mergers of neutron stars. Over billions of years, these events mix together, creating an interstellar medium with a fairly standard chemical blend, a galactic soup that gets richer with each generation. The weird region in the tadpole breaks this pattern. Spectroscopy, the art of splitting light into a rainbow to read its barcode, reveals the imbalance. Perhaps the oxygen level is unusually high compared to iron. This points directly to a sudden, localized overdose of massive star deaths. Imagine a neighborhood where, for a few million years, only the most gigantic stars were born and died. Each one exploded as a core collapse supernova, pumping out vast amounts of oxygen but relatively little iron. Their collective pollution would drench that region of space in a specific elemental signature, like a factory district where the air smells overwhelmingly of one particular chemical. Alternatively, the anomaly could show a shocking deficit, a region that is strangely pristine. If the collision ripped out a pocket of gas that had been sitting dormant in the galaxy's outer halo, untouched by generations of stars, it would be poor in all heavy elements. Mixing this primordial gas with the enriched material of the disk would dilute the expected ratios, creating a patch of space that looks younger, chemically speaking, than the galaxy that surrounds it. Each possibility tells a different story about the collision's aftermath. A pollution event marks a site of frenzied, monochromatic star formation triggered by the impact shock waves. A pristine influx reveals the deep, unmixed bones of the galaxy being churned to the surface. By reading this single, strange chemical signature, astronomers can perform a kind of cosmic archaeology, determining not just what happened in the tadpole, but in what order and from which original reservoir of material this strange piece of the puzzle was drawn. The clock is already ticking on a future tremor in spacetime itself. Deep within one of the tadpole's dense star clusters, two massive stars are locked in a decaying orbit, a partnership that can only end in a silent, universe-shaking crash. This is not a black hole binary yet, but its direct predecessor, a gravitational wave source progenitor. The system likely began as a pair of brilliant, hot O-type stars, each dozens of times more massive than our Sun, born together from the same turbulent gas cloud. Their immense gravity binds them tightly, whirling around a common center of gravity in a dance measured in days, not years. Their fate is sealed by their own brilliance. Living fast, they will exhaust their nuclear fuel in just a few million years. One will die first, collapsing in a supernova to become a neutron star or a stellar mass black hole. Miraculously, the binary bond can survive even this cataclysmic event if the explosion is symmetric enough to avoid kicking the system apart. The surviving star then evolves, swells, and eventually explodes itself, leaving behind a second dense corpse. The result is a binary system of two neutron stars, or a neutron star and a black hole, now orbiting in an even tighter, darker embrace. With no stellar winds to push them apart, their orbit begins to decay through the relentless emission of gravitational waves. These are ripples in the fabric of spacetime itself, predicted by Einstein, that carry energy away from the system. This loss causes the two objects to spiral inward, slowly at first, then with increasing frenzy over millions of years. The tadpole's chaotic environment is a perfect factory for creating such doomed pairs. The collision that shaped the galaxy triggered the formation of those incredibly dense young star clusters. In these packed stellar cities, gravitational interactions between stars are constant. Close encounters can readily bind massive stars together into tight binaries, or harden the orbits of existing pairs, setting them on the fast track to merger. Furthermore, the abundance of massive stars in these clusters means the raw materials for these cosmic time bombs are being produced in bulk. The increased rate of massive binary formation here suggests that the tadpole and galaxies like it may be significant contributors to the gravitational wave background of the universe, a faint hum of ripples from countless mergers across cosmic time. While we cannot see this particular binary yet, its final chapter is still millions of years in the future. Its existence is a statistical certainty given the environment. It represents a frozen moment in a countdown to an invisible cataclysm, a promise that the galaxy's violence will one day be expressed not in light, but in the very stretching and squeezing of the cosmos. The long tail of the tadpole is not just a river of newborn suns, it also holds a quiet, fading memory of a much older fire. Drifting as a faint, diffuse smudge against the darker void is a cluster of stars that has long since gone silent. This is a fossil star formation region, a celestial graveyard where the frenzy of creation ended billions of years ago. Its stars are not the brilliant blue of youth, but the cooler, reddish glow of old age, spread out in a loose, ghostly association. The key to its story is not in its current state, but in the uniform age of its inhabitants. When astronomers analyze the light from these thousands of stars, they find something remarkable. Every single one appears to have been born at roughly the same time. There is no mix of young and old here, no sign of multiple generations. This cluster experienced one single catastrophic burst of star formation, a brief, glorious firestorm that ignited all its suns in a relatively short cosmic span, and then nothing. The gas cloud that birthed them was either completely used up in that frenzy or violently stripped away, leaving no fuel for a second act. This fossilized burst is a time capsule, and its age is the critical clue. By measuring the precise colors and brightness of its stars, astronomers can date that ancient starburst. The evidence suggests this cluster's great birthday party happened not during the recent collision that created the tadpole's tail, but billions of years before it. This object is a relic, a surviving piece of the smaller intruder galaxy's original structure. Imagine this cluster as a quiet, elderly neighborhood that was once a booming, vibrant city district in a now vanished galaxy. When that dwarf galaxy was torn apart, most of its stars were strewn into the tidal streams, but this particular cluster, bound tightly by its own gravity, held together. It survived the galactic wrecking ball largely intact and now orbits within the tadpole's halo as a preserved piece of pre-collision history. Its very existence allows us to perform a kind of cosmic genealogy. By studying its chemical makeup, the specific elements present in its ancient stars, we can trace its lineage. Does its metal content match what we'd expect from the tadpole's own old halo stars, or is it distinctly different, carrying the unique chemical signature of its original, devoured home galaxy? This fossil cluster is therefore more than a retired nursery. It is an archaeological dig site. Its uniformly old stars tell us about the conditions in a galaxy that no longer exists, revealing that even that doomed dwarf had its own epoch of intense, focused star formation long before it ever met the tadpole. It is a silent witness to a chapter that was already ancient history when the collision began, proving that the violence we see today is just the latest act in a saga written across billions of years. What other forgotten stories from lost galaxies are hiding in plain sight, disguised as mere smudges of ancient light? A dying star refuses to fade alone, choosing instead to feed a strange and beautiful partnership. This is a symbiotic star system, a cosmic marriage of opposites locked in a gravitational embrace, their shared life creating a nebula of spectacular complexity. The partners could not be more different. One is a swollen red giant, a star in its twilight years that has puffed up to 100 times its original size, its cool, tenuous outer layers slowly bleeding away into space. The other is a hot, dense stellar corpse, a white dwarf no larger than Earth but containing the mass of a sun, a searing ember of degenerate matter. They orbit each other in a slow, intimate dance, separated by a distance perhaps comparable to that between our Sun and Jupiter. This proximity is the key to the strangeness. The red giant is so bloated that its outer atmosphere falls within the white dwarf's gravitational reach. A relentless stream of hydrogen-rich gas is pulled from the giant, flowing toward the dense white dwarf like a celestial river. This stolen material does not fall directly onto the white dwarf's surface. Instead, it forms a vast, whirling accretion disk, a flat, superheated maelstrom spiraling inward. The white dwarf, bathed in this fresh fuel, becomes the system's powerhouse. Its intense radiation and the friction within the disk heat the surrounding gas to incandescence, causing the entire region to glow with the fierce light of ionized hydrogen and helium. The result is a shared, luminous nebula that envelops both stars, a common envelope born from theft and energy. But this relationship is not stable. It is punctuated by slow, recurring eruptions. The accreted hydrogen piles up on the white dwarf's incredibly hot surface. Over decades or centuries, the pressure and temperature at the base of this layer grow until they cross a critical threshold. Suddenly, the accumulated hydrogen ignites in a runaway thermonuclear explosion. The system does not detonate like a supernova. It undergoes a nova outburst, brightening by 10,000 times or more for several weeks as the stolen layer is blasted back into space. This ejected material expands, interacting with the existing nebula and the red giant's own stellar wind, sculpting new, intricate filaments and shells within the glowing cloud. Each eruption adds a layer to the nebula's history, like rings in a tree trunk. Over millennia, these repeated outbursts can build a nebula of stunning, nested complexity, a fossil record of the system's long-term, volatile relationship. This symbiotic dance is a temporary phase destined to end in one of two ways. The white dwarf could eventually accrete enough mass to push past a critical limit, triggering a much more violent final explosion as a Type 1, a supernova. Alternatively, the red giant may finally exhaust its envelope entirely, shrinking back to leave a second white dwarf, turning the system into a silent binary of two dead stars. For now, this strange object is a laboratory of stellar interaction, a slow-motion spectacle where theft, fusion, and eruption weave together to create one of the cosmos's most intricate and patient works of art. The galaxy's grandest structures are built from threads of pure cold. Within the tadpole's turbulent clouds, where infrared blobs glow with hidden heat, there exists a skeleton of profound chill. This is a light-year-long molecular filament, a river of darkness so cold and dense it maps the galaxy's hidden architecture. To our eyes, even through the most powerful optical telescopes, this region might appear as a simple void, a black patch against the glowing nebula. But switch to a radio telescope tuned to listen for the faint whispers of specific molecules, and the void comes alive. It resolves into a delicate, sinuous thread, a backbone of gas and dust where temperatures hover just a few degrees above absolute zero. This filament is not made of the simple hydrogen that fills most of space. It is a complex boulevard of molecules where atoms have linked together in the frozen quiet. Carbon monoxide is a prime tracer, its distinct radio signature allowing astronomers to chart the filament's length, density, and motion. But it is joined by a ghostly chemistry of other compounds, water ice clinging to dust grains, methanol, and even simple organic molecules, all frozen solid onto microscopic motes of silicate and carbon dust. This dark river is the true raw material of creation, the cold storage from which stellar nurseries are stocked. Its immense length is not an accident, but a direct result of the galactic collision. The shockwaves that raced through the Tadpole's gas did not just trigger star formation randomly. They acted like a giant comb, sweeping and compressing the diffuse interstellar medium into these long, dense tendrils. The physics is one of slow, inevitable collapse. A filament this massive is held in a precarious balance between its own inward pull of gravity and the faint internal pressure of its cold gas. But gravity is patient. Over time, the filament becomes unstable to its own weight. It begins to fragment, pinching off at regular intervals along its length like a string of sausages. Each of those dense knots, known as cores, continues to contract, its internal pressure and temperature rising as it draws material in from the filament around it. Within these dark wombs, the first faint protostars ignite, their nuclear furnaces flickering on one by one. The result is a beautiful and direct correlation, a stellar assembly line. The filament becomes a string of pearls, with each luminous pearl a newborn star or a tight cluster of siblings, all born from the same dark, snaking spine. We are seeing, in a single structure, the direct link between the galaxy-scale violence of a collision and the intimate, local process of star birth. This filament is more than a nursery. It is a blueprint proving that the universe builds its greatest lights along lines drawn in cosmic frost. Even a galaxy being devoured can hold onto its heart for a while. Among the faint, unraveling streams of the intruder dwarf, a dense knot of ancient stars and dark matter may still cling together, a ghostly echo of what it once was. This is the transient galactic nucleus, the fading core of the devoured galaxy, now orbiting the tadpole like a captive king. It is no longer a true, independent center of power, but it is not yet fully dissolved. Its gravity, while diminished, remains a significant force in its local region of the tidal wreckage. This creates a fascinating gravitational anomaly, a secondary point of influence within the larger galaxy's already chaotic field. Imagine a powerful magnet slowly moving through a tray of iron filings. Its passage stirs and organizes the metal around it. The transient nucleus acts in a similar way on the gas and stars in its vicinity. As it plows through the tidal streams, its gravity can compress and shear the material, potentially triggering pockets of star formation along its path. It might be responsible for some of those isolated, brilliant knots of blue stars we see not in the main tail, but in the fainter stellar streams around it. Each burst of new suns would be a final, defiant act of creation from a dying galactic heart, using the last of its stolen material to ignite new lights before it goes dark. But this is a temporary state. The nucleus is on a decaying orbit, slowly spiraling inward toward the tadpole's supermassive black hole. With each pass, tidal forces strip away more of its outer stars, whittling it down to an ever denser core. The end game is a slow, cosmic consumption. Billions of years from now, this surviving kernel of the Dwarf galaxy will merge with the Tadpole's central bulge, its stars becoming indistinguishable from the halo, and its own central black hole, if it had one, will eventually spiral in to merge with the primary monster. That final merger will send ripples through spacetime itself, a gravitational wave signature of a meal completed. For now, this faint, wandering heart is a fossil in motion, a last piece of galactic identity refusing to be erased, teaching us that even in destruction, the echoes of structure persist, shaping new creation right up to the moment they are finally swallowed by the dark. A supernova remnant shockwave is a factory for the universe's most energetic bullets. Racing outward from the ancient explosion at thousands of kilometers per second, this wall of plasma acts as a natural, continent-sized particle accelerator. The physics is one of relentless, chaotic surfing. Protons and electrons, the raw nuclei of atoms and their lighter counterparts, become trapped in the tangled magnetic fields that are woven through the expanding shell. They are caught in the no-man's land between the relatively still interstellar medium and the violently advancing shock front. As the shockwave plows into the surrounding gas, it creates a turbulent zone where magnetic field lines are twisted, broken, and reconnected. A stray proton gets caught in this maelstrom. It bounces back and forth across the shock front, not just once, but thousands upon thousands of times. With each crossing, the moving magnetic fields of the shock itself give the particle a tiny kick, a minuscule boost of energy. Over days and weeks, these micro-kicks add up, accelerating the proton to velocities that are a significant fraction of the speed of light. Eventually, the magnetic trap can no longer hold it. The particle breaks free, now a cosmic ray, a single, ultra-fast atomic bullet screaming into the galactic void. This process, known as diffusive shock acceleration, is how a single supernova remnant can act as an engine for high-energy particles. But the Tadpole offers another, even more potent site for this acceleration, near its awakened galactic core. Here, the environment is defined not by a single expanding shell, but by the sustained, chaotic fury of the central black hole's influence. The relativistic jets, if they exist, or the intense magnetic fields churned by the accretion disk, create a region of sustained, violent turbulence. Particles can be accelerated not just at a single shock front, but through repeated encounters with magnetic whirlpools and reconnection events over a much larger volume. This can potentially boost particles to even higher, more extreme energies. The cosmic rays produced in both locations then embark on an epic journey. They spiral along the faint magnetic field lines that thread the entire Tadpole Galaxy, their paths bent into corkscrews, making it impossible to trace them back to their source. They permeate every cubic light-year, a silent, invisible rain of atomic shrapnel. When one of these high-energy protons, traveling at nearly light speed, finally collides with a stray atom in the interstellar medium, the result is a miniature fireworks show. The collision shatters both particles, producing a cascade of secondary particles and a flash of gamma-ray light. This is the final, detectable signature of a process that began in the heart of a stellar explosion or the maelstrom of a galactic core. These cosmic rays are more than just high-speed projectiles, they are vital agents of change. Their relentless bombardment helps to ionize gas clouds, influencing the chemistry of future star-forming regions. They may even play a role in triggering the collapse of those clouds by increasing the ionization that allows magnetic fields to couple to the gas. In a very real sense, the violent deaths of stars and the fury of black holes are not just destructive, they are generative forces, seeding the galaxy with the energetic particles that stir the pot of creation itself. Our final mystery is not something we see, but something we do not. It is a ghost predicted by theory, a phantom galaxy that should be there, yet remains stubbornly absent. This is the missing ultra-diffuse galaxy, the 50th and perhaps most thought-provoking strange object in the Tadpole's long tail. theoretical models of galactic collisions have long suggested a fascinating possibility. When vast streams of gas and stars are pulled into a tidal tail, the physics of the collapse can sometimes produce not just the brilliant, compact dwarf galaxies we have already found, but also their polar opposites, galaxies of profound subtlety. An ultra-diffuse galaxy is exactly what its name implies, a collection of stars as large as the Milky Way in terms of breadth, but containing only 1% of its stars. Imagine a cosmic watercolor painting where the pigment is spread so thinly across the canvas that the entire image becomes a faint, ethereal wash of light, almost indistinguishable from the background darkness. These are ghostly, transparent islands where stars are so few and far between that you could fly a spaceship from one side to the other and rarely pass near another sun. The emptiness is breathtaking. According to some simulations, the specific conditions in a massive, long-lived tidal tail like the tadpoles are perfect for forming these delicate giants. The gas is stretched thin, and the collapse happens slowly over vast areas, preventing the frantic, concentrated star formation that makes a typical dwarf galaxy shine brightly. Instead, you get a gentle, widespread drizzle of star birth, resulting in a huge, faint, and incredibly diffuse stellar cloud. Astronomers have indeed found such ultra-diffuse galaxies orbiting other large galaxies, often in clusters. But in the tadpole's tail, a place that seems to have every other predicted product of a collision, this specific ghost has not yet materialized in our telescopes. Its absence is itself a strange object, a silence in the data that speaks volumes. This missing galaxy forces us to question our assumptions. Perhaps the tadpole's tail is still too young, and given another few 100 million years, such a diffuse giant will slowly condense from the quieter pools of its stellar stream. Or maybe our simulations are missing a key piece of physics, something about the specific temperature, magnetic fields, or dark matter content of this particular tail that prevents the ultra-diffuse formation pathway. It could be that one is already there, but is so faint, so perfectly blended with the background glow of the tidal stream itself, that our current instruments simply cannot separate its whisper from the cosmic noise. This elusive non-discovery is a perfect, humbling note to end on. After a journey through 50 wonders, from screaming black holes to stellar cannibals, we are reminded that the universe always holds one more card close to its chest. The Tadpole Galaxy, for all its revealed chaos, still keeps a final, quiet secret. Its longest tail may yet hold a ghost, a vast and silent island of lost suns waiting for a future generation with sharper eyes to finally bring it into the light. This single, long-tailed galaxy has become a universe in miniature, a cosmic cabinet of curiosities holding everything from stellar cannibals and phantom black holes to newborn island universes and echoes of the Big Bang itself. We have wandered through its spiral arms and along its river of stars, counting 50 strange objects that defy simple explanation. Each one is a chapter in a grander story, a story of how chaos begets creation. The runaway star fleeing its birthplace, the ghostly dark matter clump drifting in the tidal stream, the brilliant green knot of primordial starburst, and the silent, waiting magnetar are not isolated oddities. They are all interconnected threads in the same tapestry, woven by the same ancient collision. The Tadpole Galaxy is a single, spectacular snapshot of processes that shape every corner of the cosmos, from the birth of planets in dusty disks to the merger of supermassive giants in galactic cores. It reminds us that the universe is not a static museum, but a dynamic, often violent workshop where destruction and creation are two sides of the same coin. So the next time you look up at the night sky, remember the long-tailed galaxy 420 million light-years away, and let its chaotic beauty rekindle your sense of wonder. If you want to keep exploring these cosmic mysteries with us, be sure to subscribe. And down in the comments, we would love to hear from you. Which of these 50 strange objects captured your imagination the most? Was it the quasar imposter, the stellar chimera, or the missing ghost galaxy? Share your favorite and let us keep looking up together.